Yeah, so far we have learned about supervised learning. Um, in supervised learning, we technically like give in supervised learning we technically give labels to the values or the records. So those labels will guide the model to train. Whereas in unsupervised learning methods, we will not have the labels in the data that we pass to the model. So that is the only difference. That's the reason we call the clustering, we call these methods as unsupervised techniques. In unsupervised learning techniques, we will not pass the labels along with the data sets. They will try to understand the patterns in the data set without the labels. So that's the reason these are called as unsupervised learning techniques. Clustering technically means like it's the name itself says that we group similar objects one into one cluster. So here we see different number of fruits. I mean different fruits combined together. So when we pass this data set to a particular algorithm, which is a clustering algorithm, what this will technically do is it will just group the similar objects into it will group the similar fruits. Okay, so here if you see, it has created as three groups with similar fruits as one group. So that is all clustering algorithms will do. How clustering algorithms will technically achieve this grouping of similar objects is something that we will see in the upcoming slides. So we have different like different techniques to group different patterns in the data. So if you take an example here, so this is a good example of understanding what clustering algorithms will technically do. Whereas what classification algorithms will technically do is they classify the new data that is given to that particular trained model. So example can be anything. If it is a spam or not spam detector, if it is an spam detector model, what it will do when we give a new record, it classifies whether that particular record is spam or not spam. Okay, so that is one case. The other case can be, let's suppose if you trained a dog classifier. So when we pass an image, it will say whether that is a dog or not. And we have seen different multi-class classifiers where it can detect multiple classes as the outputs and all that stuff. So that is all classification is. In clustering, the only output that you can expect from these algorithms is a grouped data. Okay, group similar objects grouped together is the only output that you can expect. If you see, if this is a good example, so different groups combined or mixed is given to this algorithm, and it is giving us the output as uh, it will give the output as unique fruits. Okay, so that is all it will actually do. Okay. And then if you look at this, clustering is an unsupervised learning technique used to group data objects into the clusters. So it is grouping data points or these data points into clusters such that data points within the cluster are more similar than those in the other clusters. So ideally, this is an ideal case. It perfectly separated all the fruits, but in real world, it may not be the case. In some cases, you will find one fruit coming up, I mean this strawberry coming up into this apple section and all that stuff. You'll see all that kind of mixing with little errors. But ideally this is the ideal case. You haven't found out any mixing up here into different groups. It's an ideal case. So it groups similar objects into one cluster. It actually will help us to do is it helps us to discover hidden patterns or structures in the data set. Okay, so you're training the model. If you are a child, you will not be able to identify every fruit looks similar to you. As you keep on growing, you will understand the difference between the fruits, and you can say which fruit is what. Okay, that's technically what clustering algorithms will do. They will try to understand the patterns in the data set, and it will form the clusters. Okay, the distance notion defines how similar or dissimilar between data points is measured. So we already have understood the distance notion, right? So we have different distance notions. We used Euclidean distances. We talked about Manhattan distances. We have talked about Mahalanobis distance and all that stuff, right? So if two objects are similar to, are close to each other, they will form a cluster, right? When two objects are close to each other, we can say they both are similar. When they are far from each other, we can say they are dissimilar to each other. Okay, so if you look at this, these are the unlabeled data set that is given to us. You can always expect unlabeled data set only for the clustering algorithms. Okay, so this is an unlabeled data set. So when we pass this data to a clustering algorithm, this is the output that is given to us. How it is actually identifying this output? This is identifying this output by calculating the, or by using the distance notion. So it takes the centroid of points, or it calculates, it picks, actually we will actually learn how this clustering will actually happen in short. But when you pass this unlabeled data set to an algorithm, it actually gives us this output where you see three clusters here. Okay, it is user defined most of the times. You tell to the algorithm like, you classify this data into these many number of clusters, because algorithm cannot decide on how many clusters that you want to form. And why algorithms will run into mess when you leave the number of clusters that you want to form to it. You will know about that shortly. Okay, so the number of clusters that you want to derive from the unlabeled data set that you pass to the algorithm is decided by the user. It's a user defined parameter. Okay, so this is how the clustering output looks like. So here you see three clusters. Green is one cluster, red is one cluster, and the yellow is the other cluster. So we formed three different clusters with the unlabeled data that you have given. Okay, so now if you talk about two different distances within this output, they are intra-cluster and inter-cluster distances. You need to understand what is intra-cluster and what is inter-cluster distance. If you look at this, intra-cluster distance is the distance between the points within the cluster. Okay, um, what intra-cluster distance will actually do is measures the distance between points within the same cluster. Okay, so intra-cluster distance is the distance within the same cluster, whereas inter-cluster distance is the distance between the clusters, between the points, between the points in different clusters. Okay, intra-cluster is the distance between points within the same cluster. Inter-cluster means, so distance between the points from different clusters, of different clusters, or whatever it is. So intra-cluster distance means it measures the distance between the points within the same cluster. Okay, inter-cluster distance means when the distance between the points, it measures the distance between the centroids or representative points of different clusters. Okay, that is called as inter-cluster distances. So representative points can be the edge of a cluster, or whatever it is, the centroid of a cluster, or the we have different, you can take any point as a representative for this cluster. And if you measure the distance between the representatives of the points between the clusters, we call that as inter-cluster distances. And now the goal of the clustering algorithms is to lower the inter-cluster distance and increase the intercluster distances. So decrease the, or lower the intercluster distances and increase the intercluster distances. So then what happens if the intercluster distance is reduced, if if the distance between the points within the cluster is reduced and distance between the points between the clusters is increased, the gap between the clusters will eventually increase, right? So you are given with two different data sets. Okay, so let's suppose these are different points given to you belonging to one cluster. Okay, and if you take another set, mm, let's take another clusters. Okay, so if you take this another cluster, okay, so this is one example, and if you take another example, so these points belongs to one cluster, and let's take the other set, and then why you will understand why we have to increase the intercluster distance uh, and decrease the intracluster distance. You will understand now. So this should be very wide. Okay, and okay. Now if you look at this, if you look at this, the intercluster distance is very less between the points. They are very tightly packed. Okay, and now intra-cluster distance is high between the points. So the centroids, when this distance is increased, what happens? Let's suppose the representative of this clusters, let's take that as centroid of these points. So this is the centroid. When you increase that distance, the distance intercluster distance, when you increase that distance, what happens? The clusters will move away from each other. When you increase this distance, the clusters will move away from each other. So there is a good partition between the patterns in the data set. In this case, the intercluster, the centroids are very close to each other. Okay. So as this is less, but intercluster distance is very large here. I mean, intra-cluster distance is very large. The distance between the points within the cluster, within the same cluster is large, but inter-cluster distance, the representative points, distance between the representative points of the two clusters is very less. So in this case, how this is looking, the cluster is there is no clear separation between the clusters. They are messing up. They are combining with each other. Whereas in this case, the distance between the points within the cluster is very less. When you keep on decreasing them, they will confine to very small circle. Okay, when you keep on decreasing the intra-cluster distances, they all confine to a very small circle. Okay, and when you take the other circle, they will confine to very large space. Just give me 1 second. So that's what it all comes down to. So we have to decrease the intra-cluster distance and increase the inter-cluster distance to make a perfect clusters. Okay, to separate the points perfectly, we need to do that. So that is what inter-cluster distance and intra-cluster distance is all about. Okay. So most of the clustering algorithms, what they will try to do is so they will try to decrease the intercluster distances and increase the intra-cluster distance. I mean, decrease the intra-cluster distances and increase the intercluster distances. In that case, we can tell that it's, so you say, suppose a clustering algorithms make clusters so that the intercluster distance between different clusters is more and intra-cluster distance of same clusters is less. In that case, we can tell that it is a good clustering algorithm. So any clustering algorithm is perfect, or we can say that is good when intra-cluster distance is reduced and inter-cluster distance is increased. So that is all about, that is all clustering algorithms will do, and this is an introduction of clusterings. Okay, clustering is an unsupervised learning technique. It actually tries to find out the similarities or dissimilarities between the points using distance notion, and distance between the points within the same cluster is called as intra-cluster distances, and the distance between the points between the distance between the points between the clusters is called as inter-cluster distances. Okay, and most of the clustering algorithms will try to decrease the intra-cluster distance and increase the inter-cluster distance. So if the clustering algorithm is doing so, we can say that as a good clustering algorithm. Okay, and right. So if we go back to the next slide, this is just an representation of that. A clustering is a partition of data set into k clusters. Okay, what it will do, what it is right now doing, it is partitioning the data D into different clusters. So each cluster will have different data points. So the cluster C1 has D1 data points, the cluster C2 has D2 data points, and cluster CK is DK data points. Clustering is breaking down or grouping the whole data set into smaller data sets where the similarity between those points in the data set is very less, which is intra-cluster distance. Clustering algorithms do not inherently know the optimal number of clusters. As we already discussed, clustering algorithms will not know about the optimal number of clusters. When you pass a data set to a clustering algorithm, you also have to specify to it that how many clusters that you need. It cannot inherently know the optimal number, even because it depends on the specific applications, data distribution, and objective. Okay, because depending on the clustering, you know it depends on your business use case. It cannot if you give it to a clustering algorithm, it can, let's suppose if you have n points in your data set, it can come up with n clusters. It can break up each point into a single cluster. Okay, it to that level it can go, but you have to specify the number of clusters that you want to break your data set into, uh, depending on your business conditions or objectives, whatever it is. So many clustering algorithms need k as an input because they aim to partition the data into fixed number of clusters. So it's a user-defined parameter. Why it is a user-defined parameter? Because the number of clusters that the user wants to derive depends on the business conditions that or the application that he is looking for the clustering and all that stuff. So it depends on the business that he is doing. Okay, if you take an example of this, consider the actual distribution of the data points in 2D plot of income versus spending score. So this is a 2D plot. Okay, here you have formed, this is the data set that is given to you. In one case, you have breakdown, you have created two clusters. So this is one cluster and this is two cluster. So in this case, you have passed K as 2 so that the clustering algorithm came up with two clusters. This is cluster number 1 and this is cluster number 2. Whereas in the other case, for the same data set, you have passed the number of clusters as 4, the parameter which is user defined, which says the number of clusters that the algorithm has to break down the data into is given as 4. Okay, in this case, it came up with 4 clusters. This is cluster 1, 2, 3, and 4. This is cluster 1, 2, 3, and 4. So it came up with 4 good clusters. Okay, why for the same data set we need 2 clusters in one case and why we need 4 clusters in one case? Okay, if you look at this example, if the customers naturally form two distinct groups, one cluster of low income, low spending, and another of high income and high spendings. Okay, so in the first case, you want to form, this is your use case. You have to form two clusters, whereas you want to differentiate the people or the customers with low income and low spendings, and also the other cluster has to be high income and high spendings. So if you look at this, this cluster belongs to high income and high spendings. So you want to break up your data into two different partitions. One is low income, low spending, and high income and high spending, so that you can run different offers to different sections of people. So when you know these are the low income people and they will spend less, you will find out the products which are of low cost and falls within their budget, and it also you can also specify the products or choose the products that they frequently bought. So you can publish those offers to this group of people, and you see these people, they will not go for low brands. So there is no point of giving offers on low brands to these people. You have to run offers on high brands or things with high values in the, so that could be the use case. So you want to break down your data set into two clusters, whereas one cluster is of high income and high spendings and the other cluster is of low income and low spendings. Okay, and if you take the other case, here you want to break down into four different clusters of different income levels with overlapping spending scores. Okay, so this is a different case. This case says you're grouping down different customers with similar spendings but different income levels. So all these customers have different income levels, right? The income falling in this range, somewhere around 10 to 25. Okay, but the spendings is almost same for all of them. They're very close. They will um, create a similar, they all have similar spendings. Okay, this is the cluster 2 where they have similar income levels and also similar spending levels. Okay, so you're breaking down or you're going down much deeper at income level. So you're grouping down into multiple income levels. So you came up with four different groups so that low products, medium products, above medium products, and high products. If you have four different categories of products that you want to s- that you want to offer to different kinds of customers. In that case, you have to go with k is equal to 4. So depending on the use case, the k value will change. Okay. Here in this case, you have only two kinds of offers. One is for high income people and the other one is for low income people. Here you have four different products for four different group of people with different incomes, right? So in that case, you want to go with k equal to 5. If you want to break much deep, much much better, like, or much lower dimensions, you can even specify k is equal to 6, so that you can even come up with two different clusters in this particular group. You can come up with two different clusters in this group, something of that sort. It is always k is always the number of clusters that the user wants, that the user looks for, is always a user specified parameter. So clustering algorithms will not be able to um, come up with a optimal number of clusters with a given data set. Okay, so that is what k parameter is. By now you understood that for clustering algorithms, the number of clusters that the user wants to form, the number of clusters that the algorithm should come up with is a user defined parameter, because k cannot be, the clustering algorithms cannot define a optimal k value. The k value also depends on the business conditions or the application of your data. So it is always a user defined parameter. Okay. And now let's talk about the distance notion. In clustering algorithms, distance notion a is always the similarity measure. I mean, not always the similarity measure. Uh, Depending on the distance notion only, the similarity of the points are decided by the clustering algorithms. What are different distance notions that are available for us? We already have known about this, but again, let's revisit this L forms. Okay, a L norms or L forms. So if you take an LP norm, which is Minkowski distance, this is the formula of the LP norm. Okay, so this is the generalized formula of distance notion or distance measure between different points. Okay, so if you apply p is equal to 1, LP norm is Minkowski distance, we call that as Minkowski distance. And when we put L is equal to 1, we call that as Manhattan distance. When we replace p as 2, we call that as Euclidean distance. Okay, when L is infinity, we call that as infinite norm. Okay, that is what LP norm is. So this LP norm will technically measure the distance between the 2 points. So if you can replace P with any value depending on the conditions or the way that you measure the distance between the 2 points. Okay, let's take the most popular ones, which is Manhattan distance, where P is equal to 1. When we replace P is equal to 1 in the LP norm, you come up with this particular formula. P is equal to 1 here, P is equal to 1 here. So it all comes down to summation of 1 to n pi minus qi. Okay, whereas L2 norm, where p is equal to 2, we just replace p with 2. So this becomes p, this p becomes 2, this becomes whole square, and 1 by p is 2, that becomes 1 by 2, which is root sigma summation of I is equal to 1 pi minus qi whole square. Okay, that is L2 norm. Infinite norm, we will come up with, let's replace p is equal to infinity, and you have to so in infinite norm, the only thing that you do is you replace p with infinity. I is equal to 1 to n pi minus qi. Pi and qi are two different points. Infinity whole to the power of 1 by infinity. Okay, so when you solve this particular equation, this limit um, equation, so you will come up with the formula as this. So it is nothing but the infinite norm is nothing but the maximum of x1 minus y1, x2 minus y2, xn minus nn. So it is just the maximum of the distances measured between two different points in the whole, I mean, in the whole points that are given to you. Okay, I'll just quickly show you an example of this infinite norm. But this Manhattan distance, when this is basically used, is often used when the movement can apply only in the horizontal or vertical directions. So when you say Manhattan distance, it tries to find out the distance between the 2 points, whereas the constraint is that you can only move in the vertical or horizontal direction. Okay, you cannot go beyond that, those 2 points. Okay, you cannot go in the cross directions or something like that. You always have to go in the horizontal or vertical directions to reach that particular point. Okay, these are the two different paths uh, of the Manhattan distance. This is part one, this is part two, where you are just moving only in the vertical or horizontal directions. You're not moving, you're not crossing the, you're not going on any other path. Apart from that, you can only walk on vertical or horizontal directions. That is called as Manhattan distance. So these are two different paths that are available. So these two will give the same values, because Manhattan distance often used when the movement only happens in horizontal or vertical direction. So any, you reach to this point anyways, any possible ways, but you can only move on horizontal or vertical directions. There are different possibilities. You can just cut over here, come back here, though this is the third way of going from point A to point B. So this distance is also similar to 1 2 3, because that is what Manhattan distance actually says. Let's say if you calculate this Manhattan distance and for these two paths, you will see that coming up to the same value. Okay, let me show you calculating the Manhattan distance between these 2 points, and then you will understand that. If you calculate the Manhattan distance between these 2 points now, so this point is 5 comma 4, right? This point is 5 comma 4. What about this point? This point is 1 comma 1. So what you have, you're given with 2 points now. Okay, 1 comma 1 and 3 comma 4. Those are the 2 points that are given to you. Now calculating the Manhattan distance via this path. Okay, just apply this formula now, and then we can come back to that particular thing. What does Manhattan distance says? Pi minus Qi. That means you have two coordinates here. That means x2 minus x1 plus y2 minus y1. So this is what Manhattan distance is. This is modulus. When you get a negative value, you just have to convert that to positive value. Now 5 minus 1 is one thing, plus x2 minus x1, and y2 minus y1, which is 4 minus 1. That comes down to 4 plus this is 3. The Manhattan distance is for this, for these 2 points, is coming down to value of 7. So the Manhattan distance now is 7, right? Now let's leave about this formula and just calculate by the graph that is available here. Now I'm just using the graph to calculate the distances. Okay. Now just send me the now just calculate the calculate using the graph that is given over here. If you calculate the distance from the graph, it looks like this now. So now we know the Manhattan distance between these 2 points is 7. Now let me calculate the distance using the graph, and it has to be equal through any path that you calculate. Okay. Now let me show you this. So this is 1, this is 2, right? This is 3. So this distance is 1. This distance is, again, you're moving horizontally 1, and you're moving vertically 1, and moving horizontally 1, and here you are vertically 1, and this is horizontally moving 2 points. So this is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So if you follow this path, it comes down to 7. Okay, if you follow this path, this is 1, this is 2, this is 3, this is 4. Or horizontally you moved 4 units, and if you go this way, 5 6 7. On vertically you moved 3 units. So 4 plus 3 is coming down to 7. Okay, 7. So it doesn't matter how you reach the point B. The only constraint with Manhattan distance is you always have to move vertically or horizontally. You can consider them as streets. Okay, in streets you cannot cross the houses, right? You can have one house here, one house here, one house here. Manhattan is like a street, right? So you cannot go over the houses. You always have to go through the routes in between the houses. So that is what Manhattan distance is. Uh, uh, so whatever path that you reach, whatever path that you take, if you take in another path, right? Let's suppose, let me just show you another path. So you have seen those two paths. Those two paths are confining to the same value that you calculated using the formula, which is sigma I is equal to 1 to n pi minus qi. Okay. Now let me take another path and show you how whether you get the same value of for the Manhattan distance or not when you only follow through horizontal and vertical directions. Okay. Now if you follow this particular path, so let's suppose I move two distances here, 3, 4, 5, 6, and 7. So even this path is given you the 7. That is what Manhattan distance is. You already aware of Euclidean distance. Euclidean distance between 2 points can be measured simply by using root of x2 minus x1 whole square plus y2 minus y1 whole square for two-dimensional sets. Okay. If it is three-dimensional, it is just simply like x1 minus x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Okay, if you have three-dimensional points, that is what Euclidean distance is. Euclidean distance, you have to understand, it is a straight line distance between the 2 points. Okay. um So that is how you calculate the Euclidean distance. Manhattan distance, you will calculate using the formula, and this is the intuition between Manhattan distance and Euclidean distance. And the third thing is calculating the infinite norm. Okay, infinite norm is x minus y infinite, right? Okay, let's understand how to calculate the infinite norm between the 2 points. Let's suppose you're giving 2 points, right? So the infinite norm is nothing but the maximum of these things, maximum of 3 minus 1 comma 4 minus 1, which is maximum of 2 comma 3, which is 3. What is the maximum value of 2 and 3? The maximum value is 3. Okay, so that is maximum of 2 comma 3. That's what we have got. 3 minus 1. One point is 3 and second point is 1. 3 minus 1, 4 minus 1, which is 4 minus 1. So that is coming down to 2 comma 3. So the maximum of these two is 3. How do we come up with this thing? This formula for infinite norm is something that you're going to understand. So you're just applying infinite for P, that is called as infinite norm out from the LP norm. So let's understand how we came up with the infinite norm. So this is the formula. Let's suppose previously the LP norm is given by sigma I is equal to 1 to n pi minus qi to the power of to the to p whole to the power of 1 by p, right? So this is the LP norm. Now replace p with infinity, and let me take xi is equal to pi minus qi. Okay, let me just eliminate this bigger term. So I'm replacing pi minus qi with xi. Okay, now it all comes down to xi to the power of p, right? So this pi minus qi is xi. So that comes down to xi to the power of p. Now, if I expand this term inside this, it is nothing but replace I with I from 1 to n, that is x1 whole to the power of p, x2 whole to the power of p, so on, xn whole to the power of p, whole to the power of 1 by p. Okay. So now I expanded the term which is inside. Okay. And now if you take this example, okay, that is what this technically means is. Okay, now take one point which is x is equal to 3 comma 1 comma 2. Let's suppose qi is equal to, if you want to understand, this is one point and the other point is 0 comma 0 comma 0. Okay, so you're trying to calculate the distance, infinite norm between these 2 points. Okay, now when you replace p is equal to 2 here, if you replace p is equal to 2 here, what it is coming down to 3 square plus 1 square plus 2 square whole to the power of 1 by 2, which is square root. So if you solve this particular equation, you're getting 3.74 is the value when p is equal to 2. When p is equal to 10, when you calculate when you replace p is equal to 10, and if you solve that equation, it comes down to x1 is 3, x2 is 1, x3 is 2. So 3 to the power of 10 plus 1 to the power of 10 plus 2 to the power of 10 whole to the power of 1 by 10. So, and if you solve this equation, you're coming down to 3.32. Okay. If you look at this, when you increased p from 2 to 10, the value got decreased from 3.74 to 3.32. And if you carefully observe this value 3.32, it is close to the maximum term within this, right? It is close to 3. And when you increase that p to infinity, this value becomes much lower and will be closer to this 3. Okay, the maximum term in this particular point that is given to you. So that is the intuition behind the formula of LP norm. LP norm, what does LP norm says? I mean, L infinity norm or infinite norm says it is the maximum of the difference between the dimensions in the points. That is what infinite norm is, and this is the understanding of the infinite norm. How we came up with that particular equation. Okay, and now if you go back to the next slide, and now we understood the basics of the clustering and also the different distance notions. Now we have to understand naive clustering algorithm. Okay, if you're given three data points, and if you are asked to cluster them, how do you cluster that? What are the different possible ways of clustering them is something that you're going to understand. This is the naive approach, which is computationally impossible, but just for our understanding. Okay, so what we do in the clustering algorithm as a step one is create all possible partitions with the given data points. Okay, you're going to create all possible clusters. Okay, creating all possible clusters means, let's suppose if you're given with three different points. Okay, if you're given with three different points, you don't know how similar they are, how similar A is to B, how similar B is to C. You're not aware of you're trying to find out that, right? You're trying to understand, you're trying to bring up the clustering algorithm's main goal is to come up with that particular grouping of similar items. But in naive partition or naive clustering algorithm, the first step is to enumerate all possible combinations or all possible clusters with the given points. I just have shown you an example of this. You are given with three different items, A, B, C, and if you want to create all possible clusterings with this, so what are the possible ways? The possible ways is you group A as similar and B and C as similar. Okay, you keep B and C as in one bin, A in one bin, and the other one is keep B in one bin and keep A and C in other bin. Okay, here I want the number of clusters to be 2. This is user defined parameter. As we already discussed, K is always user defined parameter. So here I just want to break down the points into two different clusters. Okay, what are the possible combinations of getting two clusters out of these points is these are the things, and I'll keep C in one cluster and A and B in the other cluster. Okay, the other way is uh, so what are the other possible combinations of these two? You can keep AB in one cluster and C in the other cluster, right? So this is a combination possible. In first cluster, you can keep AB, and in the second cluster, you can keep C. If we call this as cluster 1, if I call this as cluster 1, and if I call this as cluster 2, you know, so this is coming down to like I'm keeping these items in cluster 1, these items in cluster 2. So if you look at these two things, these two are similar, right? We are not the A, B and C in cluster 1, cluster 2 is same as grouping. I mean, differentiating them is same, right? C, A, B is nothing but A, B and C. So you don't need to consider them as different. Okay, so this you came up with two clusters. In one of the clusters you are keeping C, and in the other cluster you're keeping as AB, right? So this is void, this is not applicable. So the number of possible clusters that or enumerations that are possible with three different items is only these three. Okay, that is what these are the possible enumerations of the points. With ABC, the possible enumerations which is the first step of naive partition clustering, is A and BC, BAC, CAB. So you came up with three different enumerations. Okay. Now that is the first step. Generate all possible ways to partition the data into K clusters. The total number of ways to partition n points into K clusters is given by the Stirling number of the second kind, denoted as S of nk. So now you are given with an, which is 3, and number of clusters k is equal to 2, and you came up with how many partitions? You came up with 3 partitions. Like, okay, if you're given with n is equal to 100 and k is equal to 5, you cannot go with this approach of actually creating the different partitions, right? You need to have one formula to understand. Okay, this is a derived formula by just doing these experiments only. So this Stirling number of second kind formula says how many different partitions are possible, or different enumerations are possible given the number of points and the number of clusters. Okay, these numbers counts the ways to partition a set of n elements into k non-empty subsets. Okay, you understand this k non-empty subsets. There is also one possibility of ABC falling into one cluster, and there is another cluster which is empty. This is also a possibility with ABC. Okay, but the Stirling number of second kind will only give non-empty subsets, because this non-empty in this case is only one, right? You group everything into one case, and when k is equal to 2, you can just keep one bin as empty. Okay, so the Stirling number of second kind will never give the points, the empty clusters. In real world, it is rare that empty clusters will be formed. When you give k a specific number, it will exactly form those many clusters without non-empty clusters. So you can go with formula. The number of clusters, the total number of partitions or enumerations possible with n points and k clusters is given by the Stirling number of the second kind, and it is denoted by the formula of S of nk. Here, where n is the number of points given, k is the clusters that are given, is given by k into S of n minus 1 comma k plus S of n minus 1 comma k minus 1. Okay, S is the Stirling number of the second kind. Okay, so these are the boundary conditions for the Stirling number. Okay, what it says: S of n comma 0 is equal to 0, S of 0 comma k is equal to 0 when k is greater than 0 and n is greater than 0. S of 0 comma 0 is 1, S of n comma 1 is 1, S of n comma 1 is 1. Okay, so these are the boundary conditions. Using these conditions, we derive the different values for Stirling constants. Okay, now if you look at this example, let's solve one of the examples. Given n is equal to 3 and k is equal to 2. Okay, I'm trying to solve this equation now so that you will understand uh, how do we solve this Stirling number of second kind. So here n is equal to given as 3. Here n is equal to given as 3. K is equal to given as 2. Now let me substitute the values here as 3 comma 2 plus sorry, this is not plus, this is equal to. So let me erase this. Uh, so S 3 comma 2 is nothing but k is given as 2. S of 3 minus 1 is 2 comma k is 2 plus S of n minus 1, which is 2 comma k minus 2 is 1. So this is equal to 2 into S of n comma n, which is nothing but 1. So this value is 1 plus S of 2 comma 1. Okay, when S of this is nothing but S of n comma 1. So this is 1. So it comes down to 2 plus 1, which is 3. Right? So this is the same thing that we have applied here. When n is equal to 3 and k is equal to 2, when we create the enumerations by choosing all the possible ways, we got 3. Using the Stirling number of second kind also, we got 3. Okay, so that is how you calculate the Stirling kind. S is equal to 3 comma 2 is equal to 2 into S of 2 comma 2 plus S into 2 comma 1, S equal to 3 comma 2. Why this? So this is wrong. Okay, this is not the equation. So we know S of 2 comma 2 is equal to 1 and S of 2 comma 1 is equal to 1. So we applied that and we got S of 3 comma 2 is equal to 3. Okay. And you can also solve another example. You can take any example technically and you can solve it. let's suppose if you want to solve in another example, you can take it you can take and solve that. Okay. Let me take and show you another example. Let's take n is equal to 5 and k is equal to 2. Okay, and let's see how to solve that. uh, Let me take um, n is equal to 5 and k is equal to 2. What is the Stirling second equation will give us? So it is nothing but s of 5 comma 2 is equal to 2 into s of 4 comma 2 plus s of 4 comma 1, right? So just replace k and n values here. K is equal to 2, n is equal to 5, 5 minus 1 is 4, k is equal to 2, k is equal to 2, n minus 1, which is 5 minus 1 is 4, 2 minus 1 is 1. Okay, now we got this. We don't have any matching boundary conditions for this. We can replace this, right? S of 4 comma 1, n comma 1, this is 1. Okay, now the final equation for is 2 into s of 4 comma 2 plus 1. Now again break down this s of 4 comma 2 into the same way. Here k is equal to 2 and n is equal to 4. Again apply the same thing. S of 3 comma k which is 2 plus s of n minus 1 which is 3 comma 1, right? 3 comma k minus 1 which is 2 minus 1 is 1. Again 4 comma 2 is broken down into 2 into s of 3 comma 2 plus 3 comma 1 is nothing but 1. Again you have to come down and find out for 3 comma 2, which is again 2 into s of n minus 1 which is 2 comma k is equal to 2 plus s of 3 comma 2 minus 1 which is 1, right? So sorry, this is 2, s of 2 comma 1, right? 2 n is equal to 3, 3 minus 1 is 2, 2 minus 1 is 1. Here n minus 1, here n minus 1 which is 3 minus 1 which is 2 and 2 is 2, right? So now if you solve this you have to finally you have to solve this. 2 into s of 2 comma 2 is 1 plus s of n comma 1 is 1, right? From this n comma n is 1, n comma 1 is 1. So the value for this is 2 plus 1 which is 3. Okay, I replace this here. So this comes down to 2 into 3 plus 1 which is 7. Again replace this s comma 4 s4 comma 2 here. So that is 2 into 7 plus 1 which is 14 plus 1 which is 15. So the total number of enumerations possible for n is equal to 5, k is equal to 2 is 15. Okay, so this is how you know the number of enumerations possible for given n number of points and k clusters. Okay, so this is the first step of naive clustering algorithm. Once you know the partitions, the total number of partitions, total number of enumerations possible for the given points, the second thing is you calculate the distances, right? You want to pick up what is the best clustering algorithm out of this. Is the enumeration 1, this is enumeration 2, and this is enumerated cluster 3. Now you have to choose what is the best cluster out of this. So these are all possible clusterings, and now you have to come up with one clustering which is best. How do you come up with one clustering which is best? You will go with distance notion. You will calculate the distance between the points or the similar points, and you want to make sure the inter-cluster distance is larger and intra-cluster distance is less, right? So this is how the second step is in the naive clustering algorithm. What we do is, in the second step, calculate the sum of squared errors for the partition xi I. Sum of squared errors measures the variance within each cluster with lower SSE indicating tighter clusters. Okay, there are two things. In clustering algorithm, we talked about intra-cluster distance and inter-cluster distance. Okay, intra-cluster distance means the distance between the points within the same cluster, or the distance between the points within the cluster to its representative. Okay, here we talked about this intra-cluster distance, right? Distance between the points within the same cluster. So here we are trying to find out the sum of squared errors which is proportional to the variance within each cluster. Okay, that means the distance between the points within the same cluster. Okay, that is what sum of squared errors is. What if you look at this particular formula for each cluster Cj, for each xi is the each for the point in each cluster. Okay, and we are calculating the sum of squared errors for every cluster. J is equal to 1 to k is the run for cluster 1 to the k number of clusters. X belongs to Cj. You're calculate for every x that belongs to cluster Cj, you're calculating the distance from the mean of that cluster to that particular point. That is what sum of squared errors means. That means for every cluster, calculate the square distance from the mean to every point for each cluster and summate all of them and sum all of them. That is what sum of squared errors is. Okay. Now, if you look at this, if you break down this formula into two different things, okay. Let me just erase all of this. So if you look at this, let me break down this formula. Now replace j is equal to 1 to k, right? Here I have two clusters. If you look at this, I have two clusters here. Now, what I'm trying to do here is, this is cluster 1 and this is cluster 2. Okay. Now, do break down this formula, right? Apply c is equal to 1 and c is equal to 2. So if you apply c is equal to 1 for every x that belongs to cluster 1, x minus mu1 whole square. The mu1 is the mean of the cluster 1. And if I apply j is equal to 2 for for every x that belongs to cluster 2, x minus mu2 whole square, whereas mu2 is the mean of the cluster. Okay, so the summation, right? So you have to sum both of them. Now x belongs to ci means for every point that belongs to ci, for every point that belongs to cluster 1, from every point to the mean, take the difference and square them. So you get the sum of squared error for this point, this point. If you do a summation for all the square distance between the points to the mean, you get sum of squared error for this particular cluster. Similarly, you'll get for other cluster. When you summate all of them, you'll get the sum of squared errors. Okay, your goal with this clustering is decrease this distances, decrease the sum of square distances. When you keep on converging them into smaller areas, the sum of squared errors will decrease so that you will see a better clustering. Okay, now what you will do, you will calculate the sum of squared errors for every enumeration that you have created here. You calculate the sum of squared errors for cluster 1, sum of squared error 1, sum of squared error for cluster 2, and you will also calculate the sum of squared error for cluster 3. And now whichever value is less, you will choose that as the cluster. Okay, that is what naive clustering algorithm is. So this is step 2. For every, you calculate the sum of squared errors. Now step 3 is keep track of minimum sum of squared errors. Maintain a record of the minimum sum of squared error encountering during the computations. This helps in identifying the optimal clustering configuration. Okay, you calculate the sum of squared error for every cluster or every enumeration that you have created in step 1 and keep track of the minimum sum of squared error. Let's suppose the value of this is coming down to 10 and the value of this is coming down to 5 and the value of this is coming down to 20. Okay, you calculate the sum of squared error for this and keep track of this. This is the lowest for now, and then calculate the sum of squared error for the second cluster. Now, and you got the sum of squared error as 5. Now remove this 5, 10, and keep this 5 and this cluster, and then go to the next enumeration. Calculate the SSE. You got this as 20, which is greater than 5. So you will ignore this. So you keep track of the minimum SSE, and at the end, output the minimum SSE clustered. Finally, output the partition with the minimum SSE score, which represents the optimal clustering according to this criterion. Okay, so this is what naive clustering algorithm is. You create all possible enumerations with the with the given data points, and then once enumerations are created, you calculate the sum of square distances. You keep track of the minimum sum of square distance, and at the end, when you iterated through all the enumerations that are created in the step 1, output the cluster with minimum sum of squared errors. Okay, so that is what naive clustering algorithm is. Understood? All right. So now, so far we have talked about introduction to clustering. what is intra-cluster distance, what is intercluster distance, why we call clustering as unsupervised learning methods, and then we have understood why the number of clusters that the user come up that you have to partition the data into is a user defined parameter, and clustering algorithms cannot come up with an optimal k value because in most of the cases k depends on the business conditions or the data or the subject or the specific application of your data and the objectives that you are trying to find out. Based on those factors, your k value will be dependent. So k is an user defined parameter. We talked about distance notations. We talked about what is LP norm, what is L1 norm, which is Manhattan distance, L2 norm, which is Euclidean distance, and infinite norm. And we also have understood the intuition behind the L2 infinite norm formula, which is maximum of the distance between the each coordinate of that particular point, the maximum of the distance between each, or the difference in the distance between each coordinate of the point. We understood the distance notions, and we also understood the derivation or the intuition behind the infinite norm. And then we understood the naive clustering algorithm, which is partitioning the data. And if you want to find out the total number of enumerations for endpoints with k clusters, that is given by the Stirling formula of Stirling number of second kind. Okay. And then the second step is calculating the sum of squared errors. When you minimize the sum of squared errors, you are minimizing the intra-cluster distance. Okay. In minimizing the intra-cluster distance is nothing but the increasing the inter-cluster distance. Okay. So that is what computing the SSE, keeping track of SSE, and then output the minimal SSE clustering. Okay. So time complexity of this enumeration. Okay. So you are enumerating n points with k partitions, right? Or k clusters. So that is given by n log n. So this is the time complexity for this naive clustering algorithm. So this is exponential to 1. So it is computationally impossible to achieve. Okay. So that is why we call it as naive clustering algorithm. It is computationally impossible because the time complexity, which is proportional to the computational power that we need, is proportional to the power of n, which is too high. Okay. Enumeration step is technically intensive because the number of possible partitions grow rapidly with the size of the data and the number of the clusters. So you are just looking at just the enumeration is this much. So technically this is computationally inachievable. So that is the reason why we call that as naive clustering algorithm. Okay. And now going back to the first clustering algorithm, which is k-means clustering algorithm. Okay. So this is computationally possible to achieve. Um, so let's understand this algorithm. What is k-means clustering algorithm and how does this actually work? Okay. Let's go step by step by understanding this k-means clustering algorithm. So this algorithm is nothing but it also depends on the distance notion. So this given a data set like this, if you're given with a data set like this, you're trying to come up with clustering these data points into different clusters. Okay. So what is that you always have to do for a clustering algorithm? You have to initialize the k value, right? You want to come up with a k value, which is a user defined parameter, to form the number of clusters at the end. Okay. The first step in k-means clustering is choose the number of clusters k. So once you choose the number of clusters as k, now I have chosen the number of clusters as 3. I want to come up with 3 clusters with this data that is given to you. So the first step in k-means clustering is when you given k is equal to 3, pick 3 random points in the given data set as centroids of 3 different clusters. Now you want to come up with 3 different clusters, right? That is what this user defined parameter k is equal to 3 says. Now, once the user defined parameter k is set to 3, you choose 3 different points or k different points from your data set as centroids of 3 clusters. Okay. So you got 10 different points here, and out of these 10 different points, I came up with three different centroids, and I assume this as the centroids of the 3 clusters. Okay. 3 is the centroid. I choose I randomly pick 3, 5, and 8. Okay, and I'll assume these as the centroids of the three different clusters. So point number 3, 4, sorry, 5, and 8. I picked 3, 5, and 8 as the centroids of the three clusters. I assumed they doesn't necessarily needs to be, you know, the true centroids, but when you iterate through multiple iterations of this algorithm, the right centroids will be found out. Okay, but the first step would be choose k different points from this data set as centroids of the k clusters. Okay, that is step number 1. And the step number 2 is assign each point to the nearest centroid. Okay, this forms k clusters based on the closest centroid. Okay, now what you do is, now you have picked three centroids, right? Okay, now you have picked three different points as three centroids of the clusters. Now calculate the distance of every point to those clusters, or to the centroids. Okay, now let me take an example. I have taken 10 comma 11 as the point. Now what I'll do, I calculate the distance of this point to the centroid of the cluster 2, the centroid of cluster 3, and centroid of cluster 1. Okay, how do I calculate the distance from that point to the centroid of that particular cluster which we have chosen in the step 1? It is just using the Euclidean distance, which is x1 minus x2 whole square plus y1 minus y2 whole square. It can be vice versa as well, which is x2 minus x1 whole square plus y2 minus y1 whole square. Now when I calculate the distance, what happens? X1 is 10 minus x2. This point you already know, which is 11 comma 9. 10 minus 11 plus 11 minus 9 whole square, which is equal to root 5. Similarly, I calculate the distance. Let's suppose this distance is root 5. This distance can be root 15. This distance can be root 25. And by just looking at this point, you can say this is close to cluster number 2, right? You assign this 0.7 to cluster number 2. Similarly, for every other point, you calculate the distance to all the centroids and assign to the centroid which is closer to it. So once you do that, you formed three clusters. Okay, you form three clusters out of all the points. So this is cluster number 1, this is cluster number 2, and this is cluster number 3. This is based on the distances from the point to the centroids that you have chosen in step 1. Okay, now you formed three different clusters in step number 2. And what you do in the step number 3 is, now initially you have chosen the centroids randomly, right? Now you have to update the centroids so that you will come up with the right clusters. Now calculate the new centroid of each cluster by taking the mean of all data points assigned to the cluster. Now in the step 2, we have assigned different points to different clusters, right? Here in this cluster you have 4 points. Here in this cluster you have 2 points. Here in this cluster you have 4 points. Now calculate the mean of those clusters now, updated mean of those clusters. How do we get the updated mean of those two clusters? What are the 2 points that you have assigned to cluster 3? 5 and 6, right? So you have assigned 5 and 6 to these points. What are the 2 points 5 and 6? 7 comma 2 is 1 point and the 8 comma 4 is 1 point. Initially this 5 is chosen as the centroid of this cluster, right? So the 5 is 7 comma 2. Now you update the centroid from 7 comma 2 to the centroid of these 2 points. Now the centroid will comes down to 7 plus 8 comma 2 plus 4 by 2. This is the centroid of the 2 points, right? So this is the updated centroid for the cluster 2. So that is what you calculate in this step number 3. Now the updated centroid is 7.5 comma 3. Initial centroid that you have chosen from step 1 is 7 comma 2, right? So you have chosen point number 5 as the centroid for cluster 3. Now you are updating the centroid from 7 comma 3 to 7.5 comma 3 of cluster 3. Similarly, you update the clusters for cluster 1 and cluster 2 as well. How do you calculate this centroid? Again, take the summation of all the points by number of points. Calculate the centroid of these points and update the cluster centroid of this cluster. Now we got the updated clusters. Again, now in the iteration 2, you will do the same process again. Now again, take all the points, repeat the assignment and update step. So second step is assignment, and the third step is updating the centroid. Okay, so you repeat this process. Now you updated the centroids, you got new centroids, and again you do the assignments of the points. Again, what you do in the assignments, again calculate the distance of every point from to every other centroid and assign that point to the cluster which is closest to it. Now Earlier, we found out that this point 4 is closer to the centroid of cluster 1. And in the iteration 2, when you got the updated centroids, you found out that point 4 is closest to centroid cluster of the centroid of the cluster 3. Now, when you update that, when you do that assignment, what you got a different cluster. Okay. Now you got different cluster. Now 4 got moved to the cluster 3 from cluster 1. So this is cluster 1, cluster 2, and cluster 3. Again, you update the centroids based on the points. Now the new centroid will be summation of 4, 5, 6, right? Now you got 4, 5, 6. So the new centroid for cluster 3 is you have to do the summation of all these things. So now 5 comma 3, 7 comma 2, and 8 comma 4 falls under cluster 3. Now you know you need to get the new centroid, which is 5 plus 7 plus 8 by 3 comma 3 plus 2 plus 4 by 3. So this is going to be the new centroid. Okay, update the centroid again, and again do the in the that you're done with iteration 2. At the iteration 2, you got this particular cluster, and you also updated the centroids. Again in iteration 3, repeat the process. uh, Calculate the distance of every point to the updated centroids and assign that point to the cluster of that particular centroid where the distance is less. So here, if you see, the distance of point 3 is closer to centroid of cluster 3 when compared to the centroid of cluster 1. So you assign the point 3 to this particular cluster. Okay, you repeat this process until the centroids converge. Okay, when you at some point you will not see the centroid getting updated anymore. At that point you will terminate this particular algorithm. So okay, this is how the k-means clustering will work. So the first step in k-means clustering is define the number of clusters that user wants to come up with, or the clustering algorithm should come up with, which is k. Once k is chosen, you pick k number of points from the data set, and you choose them as the initial clusters. Okay, once you choose them as the clusters, in the second step, assignment, you calculate the distance of every point to the centroid of the clusters and assign them to the centroids, and then assign the point to that particular cluster where the distance from that point to the centroid is less. And in the third step, update the centroids. Calculate the new centroids and update the centroids. Again, iterate the process of assignments and update. Now, from the new centroids, from the updated centroids, calculate the distance to every point and then assign the point to the respective clusters. So you terminate this algorithm when you see the centroids got converged at some point. At some point, you no more see the centroids changing, or the values of the centroids changing, or that there you can also set a threshold such that the centroids doesn't change or exceed this threshold. The distance from this is the new centroid and this is the old centroid. If the centroid distance is less than something like 0.05, if it is less than 0.05, you terminate the algorithm, or when you don't see any change in this centroids, you terminate that algorithm. Okay, or you can also terminate the algorithm after fixed number of iterations. Let's suppose you set this algorithm to terminate after 5 iterations. You can also terminate that way. Okay, so this is all about k-means clustering algorithm. Okay, which is a basic clustering algorithm and which is widely used across so many applications. But there is a small problem with this k-means clustering algorithm. K-means clustering algorithm is an heuristic method. Heuristic method. Why? What is heuristic method is, heuristic methods do not guarantee finding a global optimal solution. It doesn't always guarantee the best clustering. Okay, that is why it is called as heuristic algorithm. It will not always give the optimal solution, global optimal solution. It may come up with a local optimal solution. Okay, heuristic methods prioritize finding the satisfactory solution efficiently rather than the perfect one. Heuristic algorithms will not guarantee the global optimal solution. In some cases it also come up with the global optimal solution. You already know what is global optimal solution and local optimal solution, right? So if you have in something like this, So this is local minimum, this is local minimum, this is local minimum, this is global minimum, right? So these heuristic algorithms will not guarantee this global optimal solution. Okay, it may come up with the it also come up with the local optimal solution. So heuristic method, when someone say this algorithm is heuristic, that means it does not guarantee the optimal global solution. Okay, heuristic methods prioritizes finding the satisfactory solution but not the perfect one. Okay, it comes up with a satisfactory solution but not the perfect one. The finer clusters are often locally optimal depending on the initial placements of the clusters. Okay, if you carefully observe the last statement, it says the output depends on the initial centroids that you have chosen. Okay, to understand that better, if you look at this, you have chosen 7, 10, and 3 as the centroids of the clusters. Okay, you have chosen 7, 10, and 3 as the these 3 points as the centroids of the 3 clusters, and the output for that for these centroids is this. Okay, which is not bad. This is also an optimal solution but not a perfect solution. Okay, now if you choose different points as the centroids of the clusters, here you have chosen 3, 7, 10, right? Here you're choosing 3, 5, and 8. Okay, you're choosing 3, 5, and 8. Here the centroid of the cluster 2 is chosen as 3. Here it is 8. Here it is centroid of cluster 1 is chosen as 7. Here it is chosen as 3. And here it is chosen as 10. Here it is chosen as 5. Now if you look at this, this is the output that you have got, right? So this is the clustering output that you have got. So when you have chosen different centroids in step 1, you're getting different outputs by the k-means clustering algorithm is give different clustering outputs. Okay, so that is why k-means clustering is called as heuristic method. It will not guarantee a global optimal solution. Most of the times it gives local optimal solution, but it is a satisfactory solution. And the solution or the output of the k-means clustering algorithm is depending on the centroids that you are choosing in the step number 1. If you just look at this, the best clustering is this is the best clustering, right? By just looking at the points. So, but in one of the solutions, it has considered all these points as one cluster, and it broke down these two things into two different clusters. But this is not a best clustering algorithm. But this is a satisfactory solution, but it is not the best clustering. This is the best clustering. Okay, but these two outputs are given by the same clustering algorithm, which is k-means. The k-means output depends on the, what do you say? Mm, depending on the centroids that you're choosing in the step number 1. All right. Okay. So how to actually solve this? Okay. How to actually solve this? Okay, let me explain you this. Let me explain you how do we come up with this. Uh, now how to solve this problem. Now clustering, you cannot just run one iteration with by choosing one by choosing like 3 different centroids in initially. When you know that k-means clustering will not give the optimal solution, it is best to iterate the whole algorithm multiple times with some parameter, with some deciding parameter, so that when you feel that is satisfactory, you can stop it, right? You doesn't conclude here by just running this. Okay, when you know that different centroids are different clusters, and we know this is not the best clustering algorithm, but it is a satisfactory solution, it's always better to repeat the whole process again and again, multiple times, so that you will reduce that error, right? You will reduce that error in the output at some point. Okay, so now how to do that is you choose this first cluster now. Okay, and within cluster sum of square distances, there are two things that we have talked about earlier as well, which is inter-cluster distance and intra-cluster distance. Okay, within cluster sum of squared errors is nothing but, what is that? It is intra-cluster distances. Now take the centroid, calculate the distance from the centroid to every point, and take a sum of that. Okay, now if you look at this, point number 8 and 10, you calculate the distance from the centroid to that particular point, 8 and 10, which is centroid is 11.5 comma 8.5, and the point 8 is 12 comma 8. If you just go back here, you'll see the point number 8. 8 is 11 comma 9, right? Calculate the distance from 11.11. 8 is 11 comma 9. The point number 8 is 11, 9. Calculate the distance to the centroid. And 10 is 12, 8. Calculate the distance from 10 to the centroid. And this comes down to the within cluster sum of squared errors. Similarly, you calculate the within cluster sum of squared errors for every cluster, for cluster 1, cluster 2, cluster 3. So the total within cluster sum of squared errors comes down to 76.83. So similarly, you calculate within cluster sum of squared errors for cluster 3, cluster 1, and cluster 2, and you summate all of them so that you will get within cluster sum of squared distances. And now between cluster sum of squared errors is nothing but how far away centroids are from the data set midpoint. Okay, now between cluster sum of squared distance is nothing but you take the centroid of all the points. Okay, you take the centroid of all the points and then calculate the distance from the centroid of each cluster to the centroid of the points. That is one way of calculating the between cluster sum of squared errors. And the other way is just summate, calculate the distance from one cluster to the other clusters and just summate them. Okay, that is other way of calculating the between cluster sum of squared errors. Okay, anyway, they both will be proportional to each other. You don't somewhere those values would be little closer. So in this case, we calculated the between cluster sum of squared distance squared error is calculated by calculating the distance from the centroid of the cluster to the centroid of the data sets. When you calculate the centroid of all these data points, this is the point that you have got. Now calculate the distance from the cluster to this centroid of the data points and summate all of them. You will get the between cluster sum of squared errors. Okay, that is within cluster sum of squared errors and between cluster sum of squared errors. Okay, now for this clustering algorithm, these are the two outputs that we have got for the k-mean clustering, right? When for the first case, when you choose different points, which is this output, okay? When you choose this different centroids, when you choose these points as the centroids, you get this cluster one. This is the output that you have gotten. This is output one, and this is output two of the k-means clustering. Now for the output one, you calculated the within within cluster sum of squared errors, right? And then you got some value which is 76.83, right, for the cluster one. And for the output two, this is output two, you got the within cluster square distances 24.5. All right. Now, right now we try, how do we conclude the best clustering algorithm? We try many different initial positions of the centroids and then we select the clustering that results in the smallest within sum of squared errors. Okay, now you iterate that process, you iterate the whole k-mean clustering with different centroids. So when you run it 3 times, you will get 3 different clustering outputs: output 1, output 2, and output 3. And for every output, you will calculate either within cluster sum of square distance, within cluster sum of squared errors or between cluster sum of squared errors. You can calculate any one of this. If you're calculating within cluster sum of squared errors, it has to be low. For the output which has the lower within cluster sum of squared errors, you choose that output. You choose that as the output of the best output of the k-mean clustering. When you're calculating between cluster sum of squared errors, whichever output has the highest value of this, whichever output has the highest between cluster sum of squared errors, you choose that as the best output by the k-means clustering algorithm. Okay, so this is how you mitigate this error of getting the best cluster with one iteration of the whole algorithm. Instead of doing one iteration, you repeat the iteration for different initial centroids and calculate the within cluster sum of squared errors or between cluster sum of squared errors for all the outputs and choose the output that is, that has minimal within cluster sum of squared errors or maximum between cluster sum of squared errors. Okay, so this is all about k-means clustering algorithm. Okay, but how to choose the optimal value for k? You know that k is an user defined parameter, right? So how to choose the best k value or the ideal k value? uh, uh, Choosing the optimal k value can also be done using the same process, okay, that we have discussed of choosing the best clustering output. So how do we choose the optimal value for k is, we call this as an elbow method, and you will understand You will shortly understand why we are calling this as why we are calling this as why we call this as uh, elbow method is this is the reason for that. So what we do is we again iterate the same process of this same process for different k values. Earlier what we have done, we have chosen different centroids, right? Now you will choose different k values and repeat this algorithm multiple times. Okay, when you choose k is equal to 1 and when you run this k mean clustering algorithm, you come up with this within sum of squared errors as 2227.3 and you plot that in a graph. For k is equal to 1, you got this as the within cluster sum of squared errors. And for k is equal to 2, run the K-means clustering algorithm and you got the within sum of squared errors. Within cluster sum of squared errors is 84.3. When you run k is equal to 3, repeat the same process, calculate the within sum of squared errors, and you got the value as 24.5. And when you calculate 4 is equal to k is equal to 4, you got 15.5. K is equal to 5, somewhere like this. At some point, the change in the values of the within cluster sum of squared errors is very less. From this point to this point, it is drastic. The within cluster sum of squared errors drastically dropped. From this point, it is little low. It is just looking like an elbow, right? When you place an elbow, it actually looks like this point where the drop got the change in the within sum of squared errors got very less. You choose that point as an optimal value for the k. So this is how you come up with the optimal value for k. And the same method, the similar method of calculating the within cluster sum of squared errors, but by choosing different centroids, you know, that is how you come up with the best clustering output. Once using this method, once you come up with the optimal k value, again iterating the same by fixing k is equal to 3, choose different centroids in different iterations and calculate the within sum of squared errors for different outputs and come up with the best clustering output. So the first step is to find out the optimal k value and the second step is to find out the best output clustering algorithm. So this is all about k-means clustering algorithm. Okay. And now to understand the difference between now if you look at the k-means clustering output, you assign each point to one of the clusters. Okay. You are not saying something like this point 6 belongs to the probability of point 6 belongs to cluster 1 is 0.9 and probability of point 6 belonging to cluster 2 is 0.1. You're not saying the probability of the point belonging to a different clusters. You are completely assigning this point to one cluster. So that is called as hard clustering. In hard clustering, you assign each data point to exactly one cluster. Okay. Data points are clearly categorized into different clusters. If you look at this, all these blue dots belongs to one cluster and all these green dots belongs to one cluster. So that is called as hard clustering. You will not say the probability or you will not try to assign each point to different clusters. You will hardly put each point into a specific cluster. So that is called as hard clustering. When coming to soft clustering, in soft clustering, we come up with the probabilities of each point belonging to different clusters. Okay. If you look at this particular diagram, we are 100% sure that all these points belongs to one cluster, but this point can go to this cluster or this cluster. There is a equal probability of this point falling in this cluster and this cluster. As you know, ideally, um, clustering algorithms will not behave in an ideal way. It cannot actually separate all the specific fruits into the same clusters. There are high chances that it may move the apple to strawberry section, something like that. It can happen. Okay, it is a mismatch or the wrongly classified clustering point. Okay, it is clustering into the wrong cluster. It clustered into the wrong cluster. But in soft clustering, we assign the probabilities. That means if you take this point, there is high confidence that this point belongs to this blue cluster. That is the reason the probability of that point belonging to the blue cluster is 0.97, which is close to 1. The probability that this point belongs to green is very less, that is 0.03. Similarly, this point has high probability of belonging to the green cluster, right? So the probability of this belonging to green cluster is 0.97, and the probability of this point belonging to the blue cluster is 0.03, which is very less. That by just looking at the data points, we can say that. But this point, this green point, right now we clustered this into the hard clustering. We clustered this point to the green cluster, but the probability of this cluster belonging to this green is 0.47, whereas the probability of this point belonging to 0. Blue is 0.53. So the only difference is that in hard clustering, we hardly assign each point to every cluster. We put every point into one cluster. Okay. Whereas in soft clustering, we come up with the probabilities of a point belonging to different clusters. Okay. If you have n clusters, we come up with n probabilities. Let's suppose if you have another cluster with color as black, we say the probability of this belonging to the black is 0.35. Okay. For that's how you come up with the probabilities of a particular point belonging to different clusters. Soft clustering assigns the probability of belonging to each cluster, allowing for partial membership in multiple clusters. So you're allowing this to be a partial member in multiple clusters, whereas in hard clustering, you're hardly assigning that to one specific cluster. Okay. Soft clustering is more detailed because it looks at how much each item belonging to different groups. It looks at this point belonging to different clusters. It gives more detailed data about a specific point. Okay. Right. So, and you can just set an algorithm. Choose only the customers where the probability of that belonging to a particular cluster is more than 0.9 or something. In that case, you will exclude this point. It does not fall into any of the clusters. All these points will fall into this cluster, and all these points will fall into this cluster. Okay. You can set a threshold so that you doesn't mix up the, like the users. Let's suppose you're running the offers again to the low spending and high spending customers. You're unsure about this particular customer belonging to the low cluster or the high cluster. Okay. In that case, you'll just drop sending offers to this particular customer. That is fine. These kind of points will be very low, and it doesn't affect much to your business. Okay. Or you can set a different kind of offer for these kind of customers where the probability of them belonging to low spendings and high spendings is equal. You can set a different kind of offer plan for these customers, and you can just send those kind of offers to those customers. Okay. So this is all about hard clustering versus soft clustering. Okay. And now, um, expected maximization algorithm is a kind of algorithm which will come up with the probabilities, or which will provide the output soft, which will I can say this is a soft clustering algorithm. Expected maximization algorithm is a soft clustering algorithm. Okay. Before going and explaining this, we can just take a short break, and then we can start this new algorithm back again. Okay. So expectation maximization is an soft clustering algorithm. So the idea behind we can call this as an methodology instead of an algorithm. So this expectation maximization methodology is used in many applications. Something like to find out the unknown values in the data set that is given, or the missing values in the data set that is given. Uh, we can find those values using this expectation maximization algorithm, but let's see how we can apply this expectation maximization algorithm in clustering. Okay. So the core idea behind this expectation maximization clustering is to iteratively estimate the probability of each data point belonging to different clusters. So we iteratively estimate the probability. Similar to k-mean clustering, how do we iteratively updated the centroids and came up with the best clustering algorithm at the end where the values got converged, right? Similar similar steps will also go over for EM algorithm as well. So what we do is we iteratively estimate the probabilities of each data point belonging to different clusters. Okay, the expectation step based on the initial guess of the cluster parameters. So and then update those cluster parameters to better fit the data based on those estimated probabilities. The maximization step, repeating until the cluster assignment stabilize and the model converges. Okay. So from this, what we understood is that we have two steps in the expectation maximization algorithm. So what we have in k-means clustering, we have assignment and update, right? Here we call them as expectation step and the maximization step. So in EM algorithm, we have two steps. One is expectation step and the other one is maximization step. What we do in the expectation stuff, in the expectation stuff, we estimate the probabilities of each data point belonging to different clusters. So that is what we do in the estimation step. And what we do in the maximization step, we update those cluster parameters to better fit the data based on these estimated probabilities. So in the expectation step, we estimate the cluster parameters. Okay. So let's suppose here, if you take this example, we came up with two clusters. Let's suppose in this case, we have chosen k is equal to 2. And we also have chosen that the data is normally distributed. Okay, that's the reason you are seeing these graphs. We considered the data is normally distributed. The probabilities of the data, the probabilities of the points belonging to the different clusters is normally distributed. So each distribution will have the parameters like mu and the standard deviation, right? Or the variance. So we have these are the parameters for the normally distribution. Based on the distribution that you have chosen, it will have its own parameters. So in the expectation step, we choose these parameters, we expect these parameters. In the maximization step, we try to maximize these parameters. Okay, or maximization is nothing but better fitting these points to the data point, better fitting or finding out the best values for this cluster parameters so that we come up with the best estimated probabilities. Okay, so this is what expectation maximization algorithm is. In the we have two steps in the expectation maximization algorithm. So the first step is expectation step and the second step is maximization step. In the expectation step, we choose the parameters for the or we estimate the probabilities of each data point belonging to different clusters. We choose the cluster parameters. Okay, that is what we estimate the cluster parameters in the expectation step. And in the maximization step, we update the cluster parameters to better fit the estimated probabilities. Okay, so we will shortly go through an example, but let's understand this. So in this initially we expected this as the cluster parameter. So this has some mean and this has some mean and this has some variance, right? And when we iterate that, the parameters got updated so that the new normal distributions are looking like this. And this is iteration 2, we got the new parameters for these probabilities. So we expected and we maximized. And in the iteration 3, we got these as the variance and the means of these 2 points. So if you look at this, these points, okay, has high probability belonging to this particular cluster, and these has low probabilities of belonging to the cluster yellow. Similarly, if you look at this has high probabilities of belonging to blue cluster, and this has less probability of belonging to blue cluster and also to the yellow cluster. So okay, so these values will give the probability of the point belonging to that particular cluster. So this is what expectation maximization algorithm is. Okay, so let's understand this by by a simple numerical example. Along with the steps that we have in EM algorithm. What we have in EM algorithm is that we first, in any clustering algorithm, we assume k clusters. right? We assume k clusters. We initialize the value of k with k clusters. Okay. So let's look at the steps in this EM algorithm now. So the first step is the initialization. So any clustering algorithm, we need to initialize the value for k, which specifies the number of clusters we want to come up with, or the algorithm wants to come up with. And the second thing is we need to initialize the parameters of the each cluster. So in GNN, which is Gaussian GM, which is Gaussian mixture model, we assume each cluster is represented by the Gaussian distribution. Okay, so for a Gaussian distribution, we will have the parameters as mean and variance, right? And along with these mean and variance, we also have another parameter called as mixing coefficient. Okay, we will understand how do we choose mixing coefficient and all that stuff. And more about this mixing coefficient shortly. But these are the parameters that we initialize when we are trying to use the CM algorithm. So based on the model of your data, if you are aware of the model, you can choose the specific model. It can be like a Gaussian model or a linear model or whatever it is. So you can choose different models if you have good understanding of your data. Okay, and then initialize the parameter or initialize the parameters. Like you can come up with some random values for this, or some set of specific values for the mean and the variance of this Gaussian distribution. And also you have to choose something called as mixing coefficient. So if you assume your data is normally distributed in Gaussian, you assume that each cluster is represented by the Gaussian distribution or normal distribution. You have the parameters like mean, covariance. So if it is two dimensionals, we say that as variance, and if it is an n-dimensional problem, you will say that as covariance matrix. And what is this mixing coefficient is that, so the proportion of points in each cluster. So the pi k, which is denoted by the mixing coefficient, is denoted by pi k, and k is the index of the Gaussian component, or you can say that as a cluster. And it is in most of the cases we will divide that into we will choose pi k as 1 by k, where k is the number of clusters. If it is three clusters, you will say pi k as 0.33. That means you're dividing, or you're assuming each portion or each cluster has equal number of points. So these are the initial values that you assign to the parameters of the cluster. So pi k is the mixing coefficient that denotes the proportion of data attributed in each cluster, right? Proportion of data attributed in each cluster. That means how many data points that will be contributed for a particular cluster. And it is denoted by the pi k. K is the index of the Gaussian component. K is the index of the Gaussian component, and pi k is denoted by 1 by k. If k is equal to 3, if k is equal to 3, the pi k will be 0.33. If k is equal to 3, it is 0.5, right? Right. So that is what mixing coefficient is. But if you have good knowledge on your data structure, and if you know that one of the clusters has 70% of your data, let's suppose you are very much aware of the data, and you know one of the cluster will be very big and one cluster will be very low. So let's suppose if you take a case where of the entire population, how many patients are not affected with corona and how many patients are affected with corona. The proportion could be 70% of the patients will be not affected with corona, whereas 30% of the population will be affected with corona. In that case, you are independent to choose the pi k value. So for the cluster 1, you can choose the pi k as 0.7, and for the cluster 2, you can choose that as 0.3. So if you have good knowledge on the data, you can choose the mixing coefficient with the respective values that you think that best fits that mixing coefficient. If not, in general, we go with 1 by k, that is equal distribution of points between clusters. Okay, so that is what pi k actually means is. So we initialize the number of clusters, the value of k, and we also initialize the parameters of the distribution. It is mean, if it is Gaussian distribution, that is mean and covariance, or the or covariance matrix, right? And also the mixing coefficient. So let's look at an example, and then you will come up with you will clearly understand how does this initialization actually work. Okay, so if you take these data points, you are given with 6 data points and you want to come up with 2 clusters. So you know the value of k is equal to 2 because you want to come up with 2 clusters, and the mean you, technically you can come up with so there it doesn't necessarily mean you have to follow a single way, but you can follow any of the ways. In this case, I have chosen the initial means as 2 and 4. That means if you carefully plot these points on a graph, you will see these two are close to each other and these two are close to each other, right? So if you actually plot this and these two diagrams, so it actually looks like this. So 1 is here, 1.5 is 1 point here, and 3 somewhere here. 5 will be here, 3.5 will be here, and 4.5 will be somewhere here. So you just take 2 as the midpoint of these two things, and you can chase 4 as the midpoint of these 3 points, right? So that's how you can come up with some means by taking the average or something of that sort. Okay. And also, and the second way of choosing the means is you can pick 2 points from the data points. You can pick 2 values from the given data set and you can consider them as a means. Okay, so mean is here in this case, in this example, we have taken the mean, or we initialize the mean with the values from the data set. Here we calculated the midpoints, or the point that is lying between these two things, between the cluster. You choose them as the means, and the variance we choose it as some random value. In most of the cases we come up with the variance as 1, so we choose that as 1. And the mixing coefficient is 1 by k, has the number of clusters is 2. Here we come up with pi 1 as 0.5 and pi 2 is 0.5. Here pi 1 is 0.5 and pi 2 is 0.5. That is how you initialize the values in EM algorithm. So this is just an example. So coming to the means, there can be many ways. You can choose the points as the data points itself as the mean, or you can also choose the midpoints, or the midpoints of the points, okay, as the mean. These are the two ways, and the initial variance can be 1 and 1, and the mixing coefficient is always 1 by k, which is 0.5 in both the cases. Okay. Most of the cases we just choose 2 random points from the data points as the mean. Okay, and then from there we will actually start. Okay, so that is what initialization is. And in the expectation step, what we do is, for each point, data point xi, calculate the probability of it belonging to each cluster k, denoted as. So you see, these are the parameters that are given. Xi and theta are the parameters of the Gaussian model. Okay, whatever model that you choose. So now you say a point, okay, belonging to the cluster. For each point xi, calculate the probability of belonging to cluster k, denoted by pi of x z is equal to k, xi comma 0 are the parameters. Okay, given the data point xi is the data point, theta is the parameters of the model, that is mean and standard deviation. And now you are calculating the probability of this point belonging to this cluster. Okay, belonging to this particular cluster k. Okay, so that is given by uh, so probability of that is given by normal distribution of that point by sum of normal distributions of the point. you know um, so it is as simple as this. Now the Bayes theorem, right? What does Bayes theorem says? Probability of A belonging to B is equal to probability of B belonging to A into posterior probability by sum of all probability of B by A, probability of A plus probability of, I mean, you summate all the possible combinations, right? All the other stuff like probability of B by A by P of P, right? You do the summation for all the clusters. So here this is denoted by probability of B given A is given by probability of this particular point belonging to this particular cluster K is given by. So this normal distribution Gaussian probability density function gives the probability of a point belonging to a particular cluster, right? So that normal distribution by normal distribution of every other cluster. Okay, so the point xi belonging to the cluster K by probability of the point belonging to to every other cluster. Okay, j running from I to K. So let's suppose if you take a simple example of this. So you're calculating the probability of a point belonging to to this particular cluster. That is nothing but probable. Let's suppose if you have three clusters, C1, C2, C3. How do you calculate the let's suppose the probability of calculating this that point belonging to this is 0.6, 0.4, and 0.1. How do you calculate the probability of a point belonging to this particular cluster? It is given by 0.6 by 0.6 plus 0.4 plus 0.1, right? The same thing that you are doing. So this normal distribution will actually gives the probability of a point belonging to that particular cluster. Okay, so normal distribution formula is given by for a normal the normally distributed the Gaussian probability density function is given by this particular formula. We learned this very long back, and we all are aware of this. So this is the normal distribution function, and you know the parameters. You initialize them in the first step itself. You know the value of mean, and you also know the value of the standard deviation, and then you can calculate the normal distribution of, I mean, Gaussian probability density function for a particular distribution. So this is how you calculate the uh, likelihood of a point belonging to a cluster. But what we have to find out here, we want to find out probability of a point belonging to, so this is similar to this, right? So this is what we are trying to find out. Probability of a point belonging to the cluster C is given by probability of xi belonging to the cluster into probability of ck by probability of this one. So now here we are trying to find out this particular stuff. And finally, we want to find out this particular stuff, the probability of a point belonging to a cluster. This is what we are trying to find out, which is posterior probability. So you want to find out posterior probability. And now in the step 2, in the expectation step, you are trying to calculate this likelihood, right? Sorry. Yeah. So in step 2, we will calculate the likelihoods. Okay. In step 2, we calculate the likelihoods. In the expectation step, we calculate the likelihoods, and using the Bayes theorem, we will calculate the posterior probability. This is the final thing that we want to calculate. Okay. So to calculate these likelihoods and to calculate this posterior probability of a point belonging to a cluster CK using the Bayes theorem. So the same thing I'm applying here. Okay. So this normal distribution is nothing but likelihood. This mixing coefficient is nothing but the prior probabilities. Okay, so once you calculate this prior probability and the likelihoods, you can calculate the posterior probability. So that is what we finally want to find out. We iteratively try to find out this posterior probability. So this is what Bayes theorem is. Now, if you look at this, prior probability is nothing but the mixing coefficient. That means probability of the cluster C1 is what probability of cluster C1 is nothing but what is that probability? Probability is nothing but probability, I mean the number of points in cluster C1 by total number of points, right? Let's suppose I have three clusters. Again, I said I have 6 points here, I have 4 points here, and I have 1 point here. So probability of cluster C1 is 6 by 6 plus 4 by 1, right? Probability of cluster C2, which is prior probability for cluster 2 is nothing but 4 by 6 plus 4 plus 1. So that is what we actually do. That is what mixing coefficient actually is, right? What is mixing coefficient is? Mixing coefficient says 1 by k. That is what we have taken the mixing coefficient, right? That means when k is equal to 2, it is 0.5. That means we are taking both each cluster has equal number of points, 5 and 5. Let's suppose we have total number of points as 10. Each cluster we conclude them as having 5 points. So that this prior probability is nothing but 5 by 5 plus 5, which is 5 by 10, which is 1 by 2, that is 0.5. That is why prior probability is nothing but the mixing coefficient. Okay, but the likelihood is nothing but the probability of given a cluster, probability of a point given a cluster. So you can have n number of clusters as I have shown you. So you're given a cluster, given this cluster, probability of a point pi is what we are trying to calculate, and that is given by, when you are given a cluster, the probability of a point xi belonging to the cluster ck is given by the normal distribution, Gaussian normal distribution, and we know the formula for the Gaussian normal distribution is this. Using this, we calculate the likelihoods, and we also the mixing coefficient is nothing but the prior probability. And once we know these two values, we can calculate the probability of a point belonging to a particular cluster. This way, we calculate the probability of all the points belonging to a particular cluster. Now let's focus on the estimation step. In the estimation step, what we calculate the likelihoods, right? So for the cluster 1, mu1 is equal to 2 and the sigma square is equal to 1. So you take this example. Here mu1 is equal to 2 and the sigma square is equal to 1. Mu2 is equal to 2 and the sigma square is equal to 1. Now, if you take these values and substitute in this equation, we get this stuff, right? Sigma is equal to 1. So that becomes 1 by the root of 2 pi e to the power of mu is equal to 2, which is xi minus 2 whole square by the 2. Sigma square is equal to 1 e to the power of minus xi minus 2 whole square by the 2. And if you take this example here, sigma is also 1 here. Mu is equal to 7, xi minus 7 whole square by the 2. So now we come up with the normal distribution equations. And now, if you calculate the likelihoods for each and every point, for x is equal to 1, replace xi is equal to 1 here and calculate this value of this whole equation, that is 0.2420. And when xi is equal to 2, calculate the value of this. So similarly, we calculate using this particular formula, substitute xi in every equation, or is this? Substitute xi in this particular formula and calculate all the likelihoods. Similarly, for the cluster 2, the probability of a point belonging to cluster 2. So for every point, calculate the likelihood of this point belonging to cluster 2. Now we got the point 1 belonging to cluster 1 is the likelihood of that is 0.2420, and the likelihood of point 1 belonging to cluster 2 is of the point 1 likelihood is 0.02 for cluster 2. This is how we calculate the likelihoods in expectation step. Okay, and now responsibilities are nothing but the which is nothing but the posterior probability. Okay, so responsibilities are nothing but the posterior probabilities, that is probability of a point belonging to a cluster c1. Ci1 is nothing but probability of a point belonging to a cluster 1. Okay, probability of xi belonging to cluster 1, right? So if ri2 is nothing but probability of a point P belonging to cluster 2. That is what R1, Ri1 and Ri2 basically means. Now we know we know the likelihoods for both the clusters for each and every point. And pi k is the mixing coefficient, which is nothing but the posterior probability, right? Prior probability, which is P of C1. Okay, now if we apply the Bayes theorem, this is the Bayes theorem. What does Bayes theorem say? Probability of A belonging to B is nothing but probability of B by A plus into P of A by probability of for all the clusters. That technically means all the clusters. So this is what Bayes' theorem actually says for us, right? So according to the Bayes' theorem, if you combine this, the probability of a point belonging to a cluster C1 is nothing but probability of the point given the cluster C into prior probability by P of B. P of B is nothing but the probability of that particular point belonging to every other cluster. If you have three clusters, I is equal to 1 to n. So this actually gives the we need to calculate the combined probability of all the stuff. That means to say, probability of, sorry, that means probability of a point belonging to cluster C1, probability of point belonging to cluster C2, and all that stuff. So N1 is nothing but the probability of a point belonging to cluster 1. N2 is nothing but the probability of point xi belonging to cluster 2. And this is the prior probability of cluster C1, probability of cluster C2. So that is what P of B is according to Bayes. So this is nothing but the posterior probability. That means probability of a point B, point xi belonging to cluster Ci. Okay, so that is what we are trying to calculate the responsibilities. Responsibilities are nothing but the posterior probabilities according to the Bayes theorem. So that is how we calculate the responsibilities. Okay. Um, Now we know N1 and N2, we know pi 1 and pi 2. Pi 1 and pi 2 is nothing but the zero point 0.5 and 0.5. When we apply all these values, when we apply pi 1, pi 2, N1, N2, we will get Ri1. So we calculate Ri1 for all the points. Ri2 is nothing but 1 minus Ri1. So if you have the probability, if you have a point the probability of a point belonging to cluster 1 as 1, the probability of that point belonging to cluster 2 will be 0. That is 1 minus Ri1. So that is how you calculate the probabilities of all the posterior probabilities of all the points. Okay, and then once you calculated these values, the next step, so this is the expectation step. In the expectation step, we calculate the likelihoods and also the posterior probabilities. And in the third step, we calculate the maximization step. This is the maximization step. What we do in the maximization step is we update the values for the parameters, which is mu, sigma k, covariance matrix, mean, and the mixing coefficient. We update these values. How do we update these values? We update these values. So we update the mean. How do we update the mean? So we calculate the posterior probability of we now we have the posterior probability, right? And we also know the point pi by posterior probabilities. This is like an expectation mean. You expectation mean and expectation variance we have calculated, right? So that is depending on the probability. So the probability of a point into that particular point by sum of all the posterior probabilities. Similarly, updating the covariance is nothing but probability by xi minus mu whole transpose by this probability. Updating the mixing coefficient is nothing but the posterior probabilities by the number of points in the within that particular cluster. So if you just look at this example, you will understand this. So the first example is updating the mixing coefficient for the particular cluster. So what we have done here, we have taken all the probabilities. Now, I mean all the responsibilities by I mean, this is the summation of all the posterior probabilities, right? We calculated the responsibilities, which is Ri1 and Ri2, Ri1 and Ri2. So this is the responsibility of cluster 1. These are the responsibilities of cluster 2. That is nothing but the posterior probabilities. Probability of a point belonging to cluster 1, probability of point belonging to cluster 2. Summate all of them by the number of points. So that becomes the responsibility of 1, and this is the responsibility of the 2. So now we calculated the mixing coefficients, mixing coefficients, updated mixing coefficients. And then the next step, we calculate the updated means. Updated means is nothing but the posterior probability multiplied by the point by sum of all the posterior probabilities. So if you just do this is nothing but the responsibility multiplied by the point plus all the responsibilities multiplied by the point by sum of all the posterior probabilities. That is updated, which is expectation mean. We already have studied about the expectation means in the first session, so in the basics. So that's how we calculate the mean for cluster 1 and updated mean for cluster 2. Similarly, updated mean for the updated variances for the cluster 1 and the cluster 2 is nothing but responsibility multiplied by the mean of this mean by the xi. Okay, what is the mean for what is the mean calculated for them? Okay, the mean calculated for the update cluster is 1.6667, right? And subtract that mean from every point that we have got. So responsibilities, updated responsibilities we got here, and the updated mean we calculated in the updated mean section. Responsibility into point minus updated responsibility whole square divided by the n. So that is how you calculate the updated means. Okay. So that's how you calculated the updated means for all the points. Okay. And then what we do now, we got all the update, we calculated all the updated values, right? Now we calculated all the updated values. Now the next step is to calculate, the yeah, now we got this. Now we calculated all the updated values. So what we have done to calculate updated values in the maximization step, these are the values. For calculating the updated mean, you multiply every point with the mean value, the posterior probability, that is the probability of a point belonging to a cluster, by summating all the responsibilities, which is nothing but the expectation mean. This is expectation variance. The probability multiplied by the xi minus mu k into xi minus mu k whole transpose by sum of all the posterior probabilities. Okay, or xi minus mu whole square for the two-dimensional data set, which is like a variance, expected variance. This is expected covariance. Okay, so once we got all the values, once we calculated all the updated values in the maximization step, again in the fourth step we repeat this process, alternate between expectation step and maximization step until the parameters converge or the improvement in the log likelihood is below threshold. So understand this, we will just come up with a small example of understanding this particular step. So we repeat this process, expectation step and maximization step. We will keep on repeating this process until the parameters converge. Parameters means mu, variance or covariance, mean, covariance, and mean, covariance, and the mixing coefficients, they all has to be equal, right? That is what we want to, once they all converge, once the parameters converge, the improvement in the log likelihood is below threshold, or the parameters converge or the improvement in the log likelihood is below threshold. Okay, the log likelihood should be below the convergence in EM algorithm happens when the parameters mean, variance, and mixing coefficient changes so little between iterations that further iterations are unlikely to improve the clustering significantly. Convergence in Young algorithm happens when the parameters mean, variance, and mixing coefficient changes so little between iterations that further iterations are unlikely to improve. So if the mean, variance, and mixing coefficient values are not changing very much from iteration to iteration, we can say that they got converged. Okay, and then we can terminate this algorithm. Okay, this stability can also be measured by monitoring the log likelihood of the data under the current parameters and stopping when the change in the likelihood is below a threshold. Okay, and the log likelihood is below a threshold, we can terminate that. Let's understood the log likelihood meanwhile, but just look at the first example. When to terminate? Let's suppose in the iteration one, these are the values of mu1, mu2, sigma 1 square. I mean variance of both the clusters and the mixing coefficients. In the iteration 2, these are the values. In the iteration 3, these are the values, and the iteration 4, these are the values. If you look at these two things, change in the values is very less here. Okay, they are here, the value is changing at decimal 1. Here the values are changing at decimal 2. So as the change in the values is very less here, we can convert the we can say the parameters got converged and we can terminate the algorithm. But let's understand what is this log likelihood now. Okay, so if you go back to the next slide, for simplicity, let's illustrate one data point x is equal to 1 for iteration 2. Okay, x is equal to 1 iteration to be calculated mean, variance, and pi 1, me 2, variance, and So cluster one likelihood is, this is the cluster one likelihood. Probability of a point one belonging to the cluster. This is the likelihood, right? So we calculate this value, we calculate the likelihoods. Weighted likelihood is nothing but pi one, which is the mixing coefficient of the point by uh, likelihood, mixing coefficient by likelihood. So log likelihood is nothing but apply the log to this. So when log likelihood is converging, we can just say, we can just terminate the application. So what do we calculate? Given the points, calculate the likelihoods of the cluster one, likelihood for the cluster two, and weighted likelihood is nothing but multiplied each posterior probability, I mean likelihood with this mixing coefficient, and then apply logarithmic to it. So in the iteration 2, if you get the logarithmic result, log likelihood as minus 12.352, and in the iteration 3 we got this value, and if you calculate the difference between these two, the difference is 0.003, which is less than the threshold that we have set. You can set threshold as any value. If that value, if the difference in the log likelihood is less than that value, we can terminate the application. So the algorithm could stop. Okay, at every step, along with the likelihoods, we also calculate the log likelihood. So we calculate the likelihoods here, right? So the likelihoods are calculated here. So these are the likelihoods. Along with the likelihoods, we also calculate the log likelihood. Log likelihood is nothing but the, we multiply this with mixing coefficients and then apply logarithmic to it. Once that value is converged, once that value got converged, we can terminate the application. Either the parameters has to be converged, or log likelihood also, at least log likelihood should get converged. So now you understood what is log likelihood, right? This stability, either the parameters has to be converged, or the stability can also be measured by monitoring the log likelihood of the data under the current parameters and stopping. So when the log likelihood got converged, we can terminate the process. So here the log likelihood got converged, so we can terminate the process here. So this is how EM algorithm actually works. In EM algorithm, it is the same steps. So in EM algorithm is a soft clustering algorithm. It's a methodology basically. So in EM algorithm, you have two steps. One is expectation step and the other one is maximization step. In the expectation step, the first step is initialization. You initialize the number of clusters. You consider the data to be a specific model, and you consider the parameters for the model. Let's suppose if it is a Gaussian model, you initialize the parameters of mean, covariance or variance, and also the mixing coefficient. In most of the cases, mixing coefficient is 1 by k, but you have good knowledge on the data, you can even assign some values to the mixing coefficients. Okay, mean can be, if you have n clusters, you can choose n different points from the given data set, or you can come up with some random values between the data sets. In most of the cases, you will just choose the n number of points or k number of points depending on the number of clusters from the data set alpha to initialize the mean. Okay, and also variance, you'll take the variance as 1 and the mixing coefficient as 2. And in the expectation step, you will calculate the likelihoods, you will calculate the prior probabilities. By using the likelihoods and prior probabilities, you will calculate the posterior probabilities using the Bayes theorem. Okay, that is what expectation step is. So once the likelihoods, posterior probabilities, and responsibilities, which is posterior probabilities, are calculated, in the third step, which is maximization step, you will update the values of mean, variance, and mixing coefficient for every cluster. So how do we calculate the mean, variance, and expected mixing coefficient, variance, and the mean? You will just calculate the expectation mean, expectation maximization, and also mixing coefficient. So these are the formulas for them. You multiply the posterior probability with every point and divided by the sum of all the posterior probabilities. You will get the mean. Variance is calculated by posterior probability multiplied by x minus mu into x minus mu whole square. And the mixing coefficient is nothing but sum of all the responsibilities or the posterior probabilities by the one. And once you got all this updated values, you repeat this expectation step and maximization step until the parameters converge below a threshold value. Okay, once the parameters converge, you can stop the algorithm. So if you see this example here there are 4 iterations, and the change from iteration 2 to iteration 3 is is more than like 0. Is around second decimal, so you can converge the algorithm. And the other stability parameter of to make the or to terminate the algorithm is calculating the log likelihood. So to calculate the log likelihood, what you have to do, you have to calculate the likelihoods and also multiply the likelihood of each cluster with its mixing coefficient and apply the log to it. Okay, once you apply the log to it, you will calculate the log likelihoods. So the log likelihood, you can say the log likelihood is converged when the change from one iteration to the other iteration is below a particular value. You can say that as, you can say the log likelihood got converged. Okay, so that is all about log calculating the log likelihoods. And that is all about EM algorithm. Now we understood, so far we have studied about clustering, what are different intercluster and intra-cluster distances, what is the goal of clustering. We have seen naive clustering algorithm, and we also have seen k-means clustering, which is hard clustering. And now we also have studied about EM algorithm, which is soft clustering algorithm. Okay. All right. And the next thing is to understand hierarchical clustering. What is this hierarchical clustering is what we will study now. Okay. Now, as we completed k-means algorithm and EM algorithm, which is soft clustering, this is another type of clustering which is called as hierarchical clustering. Hierarchical clustering is a method of clustering that seeks to build a hierarchy of clusters. That means groups data into tree-like structures called dendrograms. Okay, it groups the data into tree-like structures. That means if you look at this, it is combining these different points into tree-like structures. If you look at this here in this particular example, we have 5 different points. Initially, it clustered these 2 points, and then it also clustered these 2 points. And this is cluster 1, this is cluster 2, and then it clustered all these 3 points into one cluster, and again at the end it clustered all these points into another cluster. Okay, so that is what hierarchical clustering means. Is clustering, hierarchical clustering is a way to find natural grouping within the data. It actually clusters every point with the other point. It forms at the end, it comes up with one single cluster, but in the underlying structure, it actually combines every point into one of the clusters. Okay, uh, that is what hierarchical clustering means. Hierarchical clustering is a method of clustering that seeks to build a hierarchy of clusters, groups data into tree-like structures. So these are called as dendrograms. It groups the data into tree-like structures, and these are called as dendrograms. Okay, it is widely used in data analysis to find natural groupings within the data. So k-means algorithm is a flat clustering algorithm. It actually groups the data into two clusters, whereas in hierarchical clustering, we come up with multiple clusters, produces a tree-like structural hierarchy. Okay, produces a set of clusters, flat. These are flat. Okay, it combines both of them. This produces a tree-like structure. It creates a tree-like hierarchical structure. So for flat clustering, we have to specify the value of k, whereas for hierarchical clustering doesn't require specifically specifying k initially. Okay, we don't need to specify the value of k initially. But why we don't have to specify the value of k initially is something that we will learn shortly. Whereas for the flat clustering algorithms, you have to specify the value of the k initial itself. Based on the value of k only, it comes up with n number of clusters at the end. Whereas for hierarchical clustering, you don't need to specify the value of k initially. You will come to know about that why we don't really need to specify the value of k initially means that you will come to know shortly. This is less flexible. Flat clustering is less flexible, whereas hierarchical clustering is more flexible, can explore different levels of clustering. That means once the hierarchical once the hierarchical clustering came up with a particular output like this, it came up with a dendrogram. You can cut the dendrogram at any point. You can cut the dendrogram here, or you can cut the dendrogram here, or you can cut the dendrogram here. If you cut the dendrogram here, you will get how many clusters? You will come up with three clusters, right? uh, when you cut the dendrogram here, you will come up with two clusters. Okay, you here every point will be treated as a cluster. If you cut here, you will come up with two clusters. If you cut here, you will come up with three clusters. Okay, that is depending on the level or the threshold at which you cut this dendrogram, you will come up with different clusters. You have the flexibility to study the data at different levels. You can study the data at this level, at this level, at this level. Whereas it has to be specified earlier itself. There is less flexible to it. When you specify k is equal to 3, then it comes up with three clusters. Whereas in hierarchical clustering, that is not the case. You have the flexibility to choose a threshold. If you want to cut the dendrogram here, you don't really need to run the algorithm all over again. You can just choose the threshold based on the dendrogram. It will give you the clusters. So that is why it has more flexibility. The examples of the different algorithms available in flat clustering is, we have studied about k-means. K-medioids is also similar to k-means. You in hierarchical clustering, you will study about agglomerative hierarchical clustering and divisive hierarchical clustering, and you will understand what is agglomerative hierarchical clustering and divisive hierarchical clustering shortly. Okay, so that is the difference between flat clustering algorithms and hierarchical clustering algorithms. So now to understand different types of hierarchical clustering, as I said, one is agglomerative clustering and the other one is divisive clustering. Agglomerative clustering starts with, it's a bottom-up approach. Okay, that means you treat every point as a cluster initially. Okay, and then you will merge the points which are close to each other continuously, iteratively merge the clusters. Okay, if you look at this particular diagram here, in the first step you treat every point as a single cluster, and then you combine the points which are close to each other into one cluster. So these two points are formed into one cluster. In the step 2, these 2 points are closer, they formed into one cluster. These two are close to each other, they formed one cluster. Similarly, in the second step, just join 2 points into one cluster which are close to each other. And at step 3, okay, join all the clusters. Similarly, you keep on joining. Now you have 3 clusters here, right? And join 2 clusters that are close to each other. Okay, join these 2 clusters that are close to each other, and then now you have 4 points. Join all the clusters, all these clusters into 1 points, and then finally come up with one cluster. Okay, that is what happens in every step. In every step, so initial step is you choose every point as a single cluster. Okay, you think every point is a single cluster, and in the step 2, combine 2 points which are close to each other. In the step 3, combine the combine the next closest 2 points. The point here is can be also a cluster here. Understood, right? So the point can also be a cluster. It doesn't need to be a single point. Now the formed cluster will be treated as a single point. If you look at this, in the first step, we will take each point as a single cluster and combine the two closest points. Okay. Now I combine these into one cluster, this into one cluster, this into one cluster, right? This into one cluster and this into one cluster. Now this cluster will be treated as a single point. This cluster will be treated as a single point. Now we calculate the distance between these two clusters, and then combine the two clusters which are close to each other in the next step. Okay. Now in the next step, I'll combine two clusters, these two clusters and these two clusters. Now again, I calculate the distance from this cluster to every other point, and to whichever it is close to, I'll combine with that particular cluster. Similarly, I calculate the distance of this cluster to every other point. Okay, and then combine it with the cluster which is closest to each other. Similarly, at the end, we will come up with one single cluster. That is what agglomerative clustering is. So the best example is here. You have different species available here, different animals: eagle, peacock, lion, bear, spider, scorpio. Okay, all of them are treated as single individual points. Now combine combine the points which are close to each other. Okay. In the step 2, we will combine the animals which are similar to each other. So birds, eagle and bird, both are birds, they're combined. Lion and bear, they're mammals combined. Spider and scorpio, more than 3 leg combined. And then in the next step, you'll combine the clusters which are close to each other. So these two are more close to each other, they are vertebrates. So they are combined. And the end, they all combined as animals. So this is what hierarchical clustering, agglomerative hierarchical clustering means. This is a bottom-up approach. In every, so from we start from we start considering each point as single cluster, and we keep on combining them until it becomes a single cluster. Okay, so you arrange, if you arrange all of them into um, what to say, if you arrange if you arrange all of them into a tree-like structure, which is called as dendrogram. Okay, what are the steps that we follow in hierarchical clustering is: compute the distance between all pair of clusters, merge the closest pair of clusters, and then update the distance matrix. You will shortly see how does this distance matrix look like and how to update that distance matrix and all that stuff with a numerical example. Then you will get a complete clarity on it. So repeat this process until you got one single cluster. Or you can also terminate this algorithm when you get when you set the desired number of clusters. Okay, the ideally agglomerative clustering comes up with one single cluster, but if you want to terminate this when you got some k is equal to 3 number of clusters. Okay, here if you want to say when you got 3 clusters you want to terminate the application, you can also do so. Okay, in the agglomerative clustering. So this is all about agglomerative clustering algorithm, which is bottom up approach. Okay, and the next one is divisive clustering, which is opposite to agglomerative clustering. In divisive clustering, we break up the cluster into smaller clusters. Okay, in agglomerative clustering, you treat every point as a single cluster, and then you will join the closest points into one cluster, and you keep on doing that until you get one single cluster. Whereas in divisive clustering, you consider you consider all the points into one cluster, and you break the cluster uh, into smaller clusters. Okay, that is why divisive clustering is technically is divisive clustering starts with one cluster containing all the data points and recursively split into smaller clusters. Okay, it treats all the points into one cluster, splits the clusters into two based on some criteria like distance or variance. Okay, so you break the bigger cluster into smaller clusters, and you repeat this process until you get each point. Okay, um, until each cluster contains one data point. You keep on doing that until each cluster contains one data point. So this is the top down approach. Divisive clustering is computationally expensive, so computational expensive. So if you look at this, this is a bottom down approach. So you start from here animals, and then you divide them into two clusters, and then you divide them into other two clusters. So you repeat this process until you get one point in each cluster. So this is called as divisive clustering, which is top down approach. So types of hierarchical clustering is agglomerative clustering, which is bottom up approach, and divisive clustering, which is top down approach. And you have seen the differences between agglomerative and divisive clustering. And now let me show you an example of numerical example of agglomerative clustering. How does this agglomerative clustering technically happens? Okay, so now you all know what happens in agglomerative clustering. In agglomerative clustering, you combine the points which are close to each other, right? That is what you do in agglomerative clustering. So the first thing is calculate the distance matrix is the first step. So once you calculated the distance matrix, you update the distance matrix, merge the closest clusters. Once the distance matrix is calculated, you merge the closest clusters and then update the distance matrix. Why to update the distance matrix is what you will understand with this example. So now I was given 5 different patients or 5 different persons with different values of their health records. Okay, so I was given with 5 patients. So these are the 5 patients that are available with me. So I have 5 different patients, and the 5 different patients has different values of diastolic BP, systolic BP, weight, height, and total cholesterol. Okay. Now, what I have to do is for every patient. Okay. So these are the values of diastolic BP for different patients. Okay. Now, what I'm going to do is, okay, what I'm going to do is, uh, I want to calculate. Okay. So these are the diastolic BP points for different patients. I have 5 different patients. These are the diastolic BPs. Now I want to find out, I have to cluster. I have to cluster. I have to create an hierarchical clustering for all these different parameters. Okay. Now the first step is I calculate the distance matrix. What is distance matrix is, um, the distance matrix is nothing but the calculating the distance between these 2 points or these two vectors. Okay, so if I calculate the distance between diastolic and systolic BP for all these patients, it comes down to 70 minus 130 whole square plus 80 minus 146 whole square, so plus 78 minus 137 whole square, 60 minus 121 whole square, plus 75 minus 134 whole square. So when you calculate the distance between these 2 points, you will get this particular value. Okay, so that is what the distance between diastolic BP and the systolic BP. If you look at this value, that is how you calculated the distance between diastolic BP and the systolic BP. Similarly, you can calculate the distance from. Okay. Similarly, you calculate the distance from diastolic BP to weight. So diastolic BP to weight can be calculated by calculating the Euclidean distance between these 2 points. That is nothing but 70 minus 100 whole square, 70 minus 100 whole square plus 80 minus 96 whole square plus 70 minus 100 whole square plus 60 minus 90 whole square plus 75 minus 106 whole square. So that's how you calculate the distance between diastolic BP and a weight. So similarly, you calculate for every other combination. Okay. So from systolic BP, so you don't really need to calculate the reverse way, right? Calculating the distance from diastolic BP to systolic BP is same as calculating the distance from systolic BP to diastolic BP. That's the reason you see all these values are blank. So this value is nothing but this value. Okay. So the distance matrix would be a symmetric matrix. Okay. So that's the reason you don't, if you calculate the distance from diastolic BP to systolic BP, the same value applies for systolic BP to diastolic BP as well, right? The same value applies for systolic BP to diastolic BP. So this value will be same as this. So this value will be same as this. So this value will be same as this. So similarly, these values will fall here. These values will fall here. So this value fall here. So that is why this is a symmetric matrix. So you don't really need to fill all these things again. And now, once you calculated the distance matrix, then what I'll do in the next step is, um, merge the clusters which are close to each other. Okay, so in this distance matrix, which two are closer, which is the smallest value? 57.1 is the smallest value. That means distance, diastolic BP and weight are more similar, right? The similarity between distance, diastolic BP and weight is very low. That means you have to form them a cluster. You have to form a cluster with diastolic BP and the weight. In the next step, if we found out that the smallest distance is 57.1, that means diastolic BP and weight are close to each other, have higher similarity. So you have to cluster them into one cluster. Okay. Now I clustered diastolic BP and the weight into one single cluster in this case. Now, if you go back here, we computed the distance matrix, merge the closest clusters. We are done with 2 steps. And the third step is update distance matrix. Now, in the third step, you have to update the distance matrix. What does that means is, now you combine the diastolic BP and weight into one cluster. Okay. Now, um, these two are merged from this matrix. So these two are merged. They combined as a single row and a single column. Now, understand this zero here. The distance from diastolic BP to diastolic BP is zero. Systolic BP to systolic BP is zero. Okay. That is what these zeros are. So all the diagonal elements for this distance matrix will always be zero. Now calculate the distance of this new cluster to every other point. Okay. Initially we have everything as a single point. You have 5 different points. Okay. 1 2 3 4 5 different points are there. Okay. Now we have 5 different points. What you have done, you have calculated the distance between every other point, right? If you calculate this as diastolic BP, this is systolic BP, this is weight, height, and total cholesterol. Okay. From diastolic BP, you calculate the distance to every other point, right? In the first step. Now, what you have done, you merged the diastolic BP and weight now. Now, you merged diastolic BP and weight to one single cluster. Okay. Systolic, weight, total cholesterol. So now I merged these two, diastolic BP and weight, into one single cluster. Okay, that is what I have done because I have got that as the lowest value. As I merged these two, which is diastolic BP and weight, are merged now. And now this acts as a single cluster. Now I have to take a representative point for this cluster and then calculate the distance of it from every other distance from that combined cluster from that cluster representative to every other point. That is what updated distance matrix technically means is. So if you take this as diastolic BP and weight are merged now, and now what we have, systolic BP is there, weight is there, total cholesterol is there. So from this new cluster, which is diastolic BP and weight, from this cluster representative, we calculated the distance to systolic BP, weight, and total cholesterol. Okay, these distances will be new, but distance from systolic BP to weight will not change. Distance from systolic BP to total cholesterol will not change because these points haven't got changed, right? Those remain the same. Now, if I go back here, if you look at this, now from my new cluster, I have to calculate the distances, right? So now from distance BP from the new cluster to, I have to calculate from this new cluster, I have to calculate the new distance to systolic BP. How do I calculate that? So now I have to calculate the distance from this cluster to systolic BP. How do I calculate that? Now, systolic BP, right? So from diastolic BP to systolic BP, the distance is 134.2, right? And now from weight to systolic BP, from weight to systolic BP, what is the, from weight to systolic BP, the distance is 85.2 plus 85.2, right? So now by 2, that is how you calculate the distance from this new cluster to every other point. So that comes down to 134.2 plus 85.2 by 2. So that is nothing but, what is the value of that? What is the value of that? So it is 134.2 plus 85.2 divided by 2, which is nothing but 109.7, right? So this is 109.7. Similarly, if you want to calculate the distance from this cluster to height, how do you calculate that particular distance again now? It is similar to this. So now from diastolic BP to height, the distance is 23.8, 232.8, and from weight to height, the distance is 179.3. So if you want to calculate the distance from this cluster to height, you have to calculate it this way: 322.8 plus 179.3 by 2. This gives you the value of 206.3. Similarly to total cholesterol, how do you calculate that? Diastolic BB to total cholesterol is 289.3. From weight to total cholesterol, it is 238. And now if you want to calculate the distance, you have to take the average of it. So 289.3 plus 238 by 2, which gives 260.3. And again, systolic BP to weight. So these values will not change. These values will remain change. Systolic BP to height will be 100.3, the same as in the previous matrix. Okay, and systolic BP to total cholesterol also remains the same. Height to total cholesterol also remains the same. So now in this new cluster, in this new data matrix, where we have one cluster already formed, the lowest distance is 66.4, right? Out of all these values, the lowest value is 66.4. Now, what this says, so height and total cholesterol are close to each other, so you have to form them into one cluster. Now, height to total cholesterol is formed as one cluster. Diastolic BP to weight is formed as one cluster from this particular matrix. Now, once you merge that, you have to update the data matrix again. How do you update that again? So, height and total cholesterols are mixed, right? Height and total cholesterol are mixed. Now, from height to total cholesterol, okay, you have to calculate the distance from now. Height and total cholesterol are merged, right? So this is height. So these two clusters are merged now. Now you have to calculate the distances from the new cluster to every other cluster. Okay, that's what you have to do. The same thing again happens. So diastolic BP to systolic BP remains the same, but diastolic BP to height and total cholesterol has to be calculated. Now, instead of total cholesterol, we got these two merged, right? Now, how do you calculate? So from diastolic BP weight to height is 206.5. Total BP weight Diastolic BP weight to total cholesterol is 263.5. So diastolic BP comma weight to height and total cholesterol is nothing but this is calculated by 206.5 plus 0.5 plus 263.65 by 2. That gives you this particular value. And systolic BP to height and total cholesterol is nothing but systolic BP to height is 100.3 and systolic BP to total cholesterol is 156.5. So that comes down to just calculating the average of those two values, right? So calculate the average of 100.3 plus 156.3 by 2. So that gives you this particular value. And now in this new updated matrix, what you have got in this new updated matrix, you got the smallest value as systolic BP, right? The smallest value is 109.7. Now you have to combine diastolic BP weight with systolic BP into one cluster. So we formed this particular cluster. Okay. And then again update the matrices, update the distance matrix. Now these two are combined into one cluster. Now the new distance matrix looks like this. Now you have to combine the distance from this cluster to this cluster. That is nothing but diastolic BP weight to height and total cholesterol is 234.85 and the distance from systolic BP to height to total cholesterol is 128.5. So average of these two will give this particular value 181.5, 181.75. Okay. Finally, what is the distance lowest that value that we have? 181.7. So combine everything into single cluster. So this is how the agglomerative clustering will happen. Finally, initially we considered every single point as a cluster, and then finally we came up with one single cluster where a hierarchy or a dendrogram is created. So diastolic weight combined to one cluster, systolic BP combined to one cluster, height and total cholesterol combined to one cluster, everything combined into one cluster, right? So this is how you form the dendrogram. All right. So this is all about agglomerative clustering algorithm using distance matrices. Now, as I said we have very high flexibility with the hierarchical clustering. Okay. More flexibility. Why we have more flexibility? Because we can explore different levels of clustering, right? So go back here. Now, look at this. Look at different points where the clusters got merged. So the initial first cluster got merged at 57.1, right? and the next cluster got merged at 66.4, but height and total cholesterol merged at 66.4. Diastolic BP and weight merged at 57.1. So these merged at 57.1, these merged at 66.4, right? The distance, right? Euclidean distance at which they got merged. And systolic BP, diastolic BP weight merged at 109.7, right? This is 109.7. They merged at 109.7. And the final cluster formed at 181.57. Okay, these are the distances. Now, if I set the arbitrary value at 150, if I set the equilibrium distance as 150, if I cut the cluster here, if I cut the dendrogram here, how many clusters we got? We got two clusters. Okay, the first cluster is systolic BP, diastolic BP, and weight into one cluster, height and cholesterol into one cluster. Okay, if I cut the threshold here, but if I cut the threshold at 100, okay, if I set the threshold at 100, I got three clusters, right? The first cluster is height and weight into one cluster, systolic BP into one cluster, diastolic BP and weight into the other cluster. So that is how the flexibility came up with hierarchical clustering. Once you created the dendrogram, you can set any arbitrary value as the Euclidean distance. Based on that arbitrary value, you will form a number of clusters. Okay. Here, if you set the Euclidean distance as 100 or the arbitrary value as 100, you came up with three different clusters. Whereas in this case, when you set the arbitrary value as 150, you came up with two different clusters. Okay. So this is all about agglomerative clustering. Okay, so we covered most of the stuff, but the one important thing here is when you updated the matrix in the previous example, when you updated the matrix, what you have done, you have taken the average, right? You have taken the average of the distance between the clusters. That means, so when you're trying to calculate the distance of a particular cluster to the updated cluster, okay, now if you formed one particular cluster, right? When you formed one particular cluster, sorry, now when you formed one particular cluster, okay, and when you are trying to find out the distance of that particular cluster to another cluster, so let's suppose I have two different points here. You found out the distance from this point to this point, this point to this point, and then you took the average of the distances, right? Let's suppose if you take this example again, okay, diastolic BP weight to systolic BP, okay, diastolic BP weight to systolic BP. What you have done, to calculate that, uh, you just take this. So diastolic BP and weight to systolic BP, right? So how did you calculate this distance? So you took diastolic BP to systolic BP, which is 134.2. So this is 134.2, and the other thing is weight to systolic BP, which is weight to systolic BP, which is 85.2. You have taken these two things. When you are trying to merge the newly formed cluster with one of the points, you have taken the distance from both the points to that particular point, and you have taken the average of these two, right? 134.2 plus 85.2 by 2, that is what you have taken. So that is one way of calculating the distance between the clusters, okay, between the clusters or the two different clusters. So we call them as linkage functions, okay, calculating the updated distances between the clusters. A linkage function determines how the distance between clusters is calculated. In that case, we have taken the average of the distances from the clusters, from between the two clusters, right? If you consider this point as one cluster and this point as one cluster, this one point as one cluster and these two points as one cluster, the distance between these two clusters are calculated by taking the average of the distances between the points, right? So that is one of the linkage functions. Okay, the linkage function determines how the distance between clusters is calculated. Okay, how the distance between the clusters is calculated is what linkage function is. This choice significantly affects the shape and structure of the resulting clusters. Okay, so this choice of the linkage function. Now let's understand what are different linkage functions that are available for us to use, and then how these linkage functions will affect the shape of the cluster or shape of the dendrogram is is what you have to understand. These will drastically affect the shape of the resulting linkage, resulting cluster based on in the previous example of in this previous example where we have solved a numerical example for agglomerative clustering, we have taken the average as the linkage function, average of the distances as the linkage function. But let's see what are the different linkage functions that are available. Okay, a linkage functions calculates between the two individual data points initially and then clusters as the clustering progresses. So linkage functions calculates the distance between two individual points initially. So because in agglomerative clustering, the first step is that every point is considered as an cluster, right? And then we calculated the distance and then we merged the nearest points and then we keep on doing that till we got single cluster. So as we progress, the distance between the classes are calculated. The linkage functions are used to calculate the distance between the clusters. Okay, what are different types of linkage functions is, the first one is single linkage or minimal linkage. In this case, distance between the two clusters is the smallest distance between any 2 points in the cluster. Okay, the distance between two clusters is the smallest distance between any two clusters in the any 2 points in the cluster. Okay, let's take this example again. So I have this one cluster, I have 1 point here, 1 point here, and this cluster has 1 point. And now the distance between these 2 points is 134 and the distance between these points is 82. Something of the sort we have got here, right? 134, 85. Okay, 134, 82. Let's take this example as 132, 84. Now to calculate the distance between these two clusters, what we have taken? We have taken the average between the distances in the previous example. But what single linkage says is that, single linkage says the distance between the clusters is nothing but the smallest distance between the points in the cluster. Smallest distance between any 2 points in the cluster. That means what is the smallest here? 134, 82. 82 is the smallest, right? So now the new distance will have 82. The new distance between the clusters is 82. So here we have updated this value 1097, 109.7 by calculating the average of these two distances, right? That's how we got 107. But when you use the linkage function as single linkage, this value will become 85.2, not 100.7. So this becomes 85.2. Okay, so that is what single linkage function will actually do. Single linkage function will consider the distance between two clusters as the smallest distance between any 2 points in the clusters. Okay, the smallest or the closest point, closest pair of items, minimum distance between all the clusters. So we calculate the distances from every point to every other point, and the smallest distance will be the is the one which we will consider as the distance between the two clusters. So single linkage says minimum of distances of x and y. Okay, where x belongs to cluster C1 and y belongs to cluster Cj. So calculate the distances between every 2 points and take the minimum of those distances, which will be the distances between the distance between the clusters, and that distance is calculated as the distance between the clusters. And these single linkages is sensitive to outliers. Let's suppose I have all my points here and one point which is outlier is staying here. This is my one cluster. Okay, so why this is sensitive to outlier is what you have to understand. And now I have another cluster somewhere here. This is my second cluster. And when you calculate when you consider single linkage as the linkage function, what happens is that when you consider single linkage as a single, so this is one cluster and this is one cluster, and you when calculate the single linkage, this is considered as the single linkage distance. That is what you consider as the distance between the two clusters. But this is an outlier which is far from the original points, and this will drastically affect the clustering. Okay, so that is the reason it is sensitive to outliers. So this single linkage function is sensitive to the outliers. The second type of linkage function is complete linkage. Complete linkage means maximum. It is opposite to single linkage. Single linkage will consider the smallest distance between the points in the between the two clusters, whereas complete linkage means the distance between the two clusters is the largest between any 2 points in the clusters. So calculate the distance between every 2 points in the cluster, and then the maximum distance would be the maximum the maximum of all those distances would be the complete linkage function. This is also sensitive to the outliers, because it is vice versa. So if you have all the points here belonging to one cluster and one is very far, and if you have the other cluster something like this coming up over here, if you have another cluster here, this is one cluster and this is the other cluster, and the complete linkage will actually calculate this distance. So this is an outlier which is considered to be part of this cluster, but that is an outlier. So when you take the complete linkage, it will actually affect the distance. It is actually affecting the distance between the clusters. Okay, so complete linkage is also sensitive to outliers. So single linkage is the smallest distance between points in the different points in the different points and different clusters. Smallest distance between two clusters will be considered is equal to the smallest distance between different points in the cluster. Complete linkage is the largest distance, right? The largest distance between distances between different points in the clusters. And now average linkage is the is less sensitive to outliers when compared to single linkage and complete linkage. What is average linkage means is that you know um, calculate the distance between every 2 points in the clusters and take the average of all those distances. Okay, so that is given by the formula. It is x belongs to cluster c1, y belongs to cluster c. Calculate the distance between x and y, and then divide that with size of the cluster 1 and the size of cluster 2. Okay, that will give you the average distance. If you look at this example, I have 3 points here, I have 2 points here. From a to I calculate the distance from A to every other point, I, J, H, N. So A to I, A to H, and A to N. Okay. And also from D to J, D to H, and D to N. D to J, D to H, and D to N. So I have taken calculated distance from this point to every other point. And how many distance I have calculated? 6 distances, right? From A to 3 and from D to 3. So that is the total number of distances. That is nothing but 2 into 3, right? The size of cluster 1 is 2, size of cluster 2 is 3. From every point in cluster 1, the distance to every other point in cluster 2 is calculated. So you divide that in the denominator by 2 into 3. So this is called as average linkage. If this is used for calculating the distance between the two clusters, we call that as average linkage function. So as we are calculating the distance, as we're considering the distance between every uh, as we're calculating the distance between every points, so outliers will have less impact, right? So you even this outlier have impact. So you're taking every other distance. So these distances are minimizing this distance. Okay, minimizing this effect of this outlier. So that is what average linkage function is. Now centroid linkage is another example of linkage functions. Okay, we are almost to the end. We will just understand. We have just 3 more slides to actually understand. With that, we will be closing this. So let me explain you what is this centroid linkage. Centroid linkage is nothing but the distance between two clusters is the distance between two clusters is the distance between their centroids. Okay, calculate the centroid of one cluster, and then the distance between the centroids is treated as the linkage distance. Okay, linkage function. So just take an example. It's very easy to understand, computationally efficient. Here, if you say average linkage, you have to calculate the distance between every 2 points, and that looks computationally inefficient, right? Because you have to calculate so many distances, right? Whereas in centroid linkage, you calculate the centroid of each cluster, and then you're calculating only the distances between the centroid, which is computationally efficient. But the problem with centroid linkage is inversion in the dendrogram occurs. When the there are inversion issues. This is computationally efficient, but less commonly used. This centroid linkage is less commonly used because of inversion issues. Okay. it has something called as inversion issues. What are inversion issues is nothing but inversion in dendrogram occurs when a newly merged cluster has a distance value or smaller than the previous merge. If you take this example, A and B merged at 2, C and D merged at 7, but the newly formed final cluster merged at 6. So there is this is called as an inversion issue. The distance of the newly formed cluster is less than the older cluster that is formed at distance 7. That is called as inversion issue. If you just look at this example, so this is called as an inversion issue. So the newly formed cluster's distance is less than the distance of the uh, you know mm, distance of the cluster previously formed clusters. So if you take when you cut at 7, you are getting only one cluster, but if you're cutting at 6, you're getting how many clusters you're getting 4 clusters. Okay, when you're cutting this at low distance, you're getting more clusters. When you're cutting this at high distance, you're getting very low clusters, right? That means sorry, you mean to say I mean to say this way. So when you cut at 6, so this is looking like this: A, B formed at one point, C, D formed the cluster at one point, but they merged here, okay, at low distance. There is an inversion issue. So when you actually cut this at a particular distance, the real analogy between of the dendrogram is failing, right? So here at this distance, if you cut at this distance, you're getting 4 clusters. If you cut at this distance 7, you're getting how many clusters? You technically, you when this has to be one cluster, but you're getting 4 clusters here, even if you cut at highest distance. Here at distance 6, you it formed a one single cluster, right? But when you cut at a distance more than 6, you're again forming how many clusters? 4 clusters again. At 6, it formed one cluster. Okay, or everything is merged at one cluster. But when you cut anything more than that, you're still getting more number of clusters. Okay, this is an inversion issue. That is a problem with centroid linkage. That means higher clusters are forming at lower distances. Just a simple example of this centroid clustering. So if you take this example, so 0 comma 0, 2 comma 0, 6 comma 0, 8 comma 0. So these are, what do you say, these are different points. Now calculate the distance between every other point. From A to B the distance is 2, from B to C the distance is 6. So from A to C the distance is 6, from A to D the distance is 8. Similarly, you calculate the distance from every other points, right? Now if you look at this, the smallest here is 2. So you merge A and B. So when you merge A and B, you take the centroid of these 2 points, which is 0, comma 0 plus 2 by 2, which is 1. 0 plus 0 by 0 is nothing but 1 by 1. So the centroid of the newly formed cluster is 1, comma 0. Now you calculate from the centroid to every other point. So from this centroid to the new point, so the distance from the centroid of this cluster AB to the new point C is 5. 6 minus 1 is 5 whole square to the power of root 2. So this becomes root of 6 minus 1 whole square plus 0 minus 0 whole square, that is 5 square, which is 5, right? So the distance is not calculated that way. So similarly, and the next says we got the lowest distance as C and D. So you calculate the centroid of these 2 points, which is 6 plus 8 by 2, which is 14 by 2, 7 comma 0. So centroid of C and D is 7 comma 0, centroid of A and B is 1 comma 0, and then calculate the distance between the centroids, which is 6. But that is the distance between the two centroids. Okay, so this is how the centroid linkage will work. Centroid linkage is nothing but the distance between the centroids of the clusters. Okay, and the problem with the centroids is inversion issue. Inversion issue is nothing but the clusters, the newly formed clusters will be when the newly merged clusters has a distance value or height in the dendrogram smaller than the previous merge. So when that happens, when you cut the dendrogram at higher value, you will not see the desired number of clusters. Okay, so that is what centroid linkage is. We talked about simple linkage, we talked about complete linkage, I mean single linkage, complete linkage, average linkage, and centroid linkage. And the last one we will be talking about is Ward's linkage. Okay, Ward's linkage is nothing but distance between two clusters is the increase in the total within cluster variance when the clusters are merged. So Ward's linkage is the most frequently computational intensive, but often provides high quality clustering. Okay, this Ward's linkage is computational intensive, but provides high quality clustering, often used in practice. So this Ward's linkage is highly used in practice. What this Ward's linkage is increase in SSE after merging, which has the highest sum of squared errors after merging, will be considered as the new distance between the clusters. Okay, distance between two clusters is the increase in wherever there is an increase in total, highest increase in the total within cluster variance. Okay, what is within cluster variance? The distance between the points within the cluster is called as within cluster variance. Okay, and the clusters are merged. Distance between clusters is the increase in the total within cluster variance. Okay, let's see an example for you to understand this better. So we calculate within cluster variance, and whichever has the highest within cluster variance, we merge them. Okay, now look at this small example. So we have four different points, 1, 2, 9, and 10. Now calculate the within cluster variance. Now if you want to calculate the within cluster variance between these two, 1 minus 2 whole square, that is sum of squared errors. From 1 minus 9 whole square, 1 minus 10 whole square. From B to C, 2 minus 9, 2 minus 10 whole square. From C to D, 9 minus 10 whole square. These are the initial distances within cluster variances. Okay, now if you look at this, the smallest here is A and B, right? So you can even merge C and D, but they both have the same value. So I'll merge A and B. Now I merged A and B. So centroid of that will become 1 plus 2 by 2, which is 1.5. Now calculate the variance. Variance is from, there are 2 points. Now we merged 1 comma 2, which are, these are the 2 points that we have merged. Centroid now is 1.5. Calculate within cluster variance. 1 minus 1.5 whole square plus 2 minus 2.5 whole square, which is 0.5. Okay. Recalculating distances to C1. Now we recalculate the distances to C1, which is centroid of C1 comma C. Okay, so this is C point, right? Now we got 2 points. So the centroid of this will represent the new cluster. Okay, now the new points that we have is 1 comma 5 for A and B. For C it is 9 and D it is 10. Now you calculate again the variances between the points. Okay, now this is one cluster, this is one cluster, this is one cluster, right? Now, when you calculate the variances, how do you calculate the variance between the points? When you calculate this, when you merge these 2 points now, when you merge these two, A, B, and C, uh, what is the increase in the variance? When you merge these two, the centroid of these two will become 1 plus 5 plus 9 by 2, which is 5.25. And then from this centroid, you calculate the distance of all the points. Okay, the centroid of all the points will become 1 comma so this is same like this. So this is the centroid of these 2 points, 1 comma 2 comma 9. Or else you can even say 1 plus 2 plus 9 by 3. That comes down to 10 12 by 12 by 3, which is okay. So So now, so this is the first merge, right? So as the distance between these 2 points is less, we calculated the variance in the data, and which is coming down to 0.5. So this is the first merge. Now when A and B are merged, we calculate the increase in the variance. Okay, increase in the I mean, this is recalculating the distances after the first merge. After the first merge is done, let me just clear everything, so I'll just explain. So we calculated the initial distances here. We calculated the initial distances here. Let me come back with some other class. Okay, so we calculated the initial distance and found this is the smallest distance. So we merged these two clusters A and B, and then we found out that the centroid of this new cluster is 1.5 and the variance is 0.5. Okay, that is, and the variance is 0.5. And what we are trying to calculate, the distance is nothing but the increase in sum of squared errors, right, after merging. The distance between the two clusters is increased in sum of squared errors after merging. Increase in the SSE, sum of squared errors after merging. So whichever has the highest value, that is considered as the newest, that is considered as the distance between the two clusters. Increase in sum of squared errors after merging. Okay, so now this is the variance within this cluster, which is formed first because the distance is less. Now recalculating the distances from the cluster C1 to the C point C. So now how to take, so the cluster has mean 1.5 and the new point is, so the cluster representative is 1.5 and this point C is 9. So you take the mean as 9 plus 1.5 by the 2, which is 5.25. So that is the mean. And now calculate the increase in the variance with this mean. So increase in the variance means you calculated the distance, square distance between with every other point. So this is the variance we got. And what is the increase in the variance? Increase in the variance is nothing but variance of the total combined cluster minus variance of this cluster, which is 36.5 minus 0.5, which is 36.0. Now merging C1 with D, we are merging cluster C1 with the point D. So now take the median again, 1.5 plus 10 by 2, which is 5.75. So this is a new centroid. Variance is calculated by, what are the 2 points that we have? 1, comma 2, right? So 1, comma 2, comma 10. We are merging C1 with D. So calculate the variance from every other point. 1 minus 5.75 whole square plus 2 minus 5.75 whole square plus 10 minus 5.75 whole square. So the new variance is 41.5 and the increased variance 41.5 minus 0.5, which is 41.0. So these are the increase new distances. Okay, the C comma distance from C to D will always remain same. So if you look at this, the increase in the variance, what is the smallest value between all these things? So 1 is the smallest value, right? So second merge will be C and D. We merge C and D since distance between C and D is 1. So new cluster is C comma D. The centroid of the new cluster is 9.5. So C and D will fall here. The centroid cluster is 9.5 and A and B falls here. Centroid of this cluster is 1.5. Now take the new centroid as 1.5 plus 9.5 by 2. Okay, 9 plus 10 by 2. Oh, sorry, the new centroid is 9.5, right? So now variance is 9.5. Within variance, the variance within C and D is 9 minus 9.5 whole square plus 10 minus 9.5 whole square, which is 0.5. Okay, the variance within this cluster is 0.5. Finally, what you do, you only merge these two clusters into one single cluster. Okay, so the new cluster will have the is this as 5.5. Increase in the variance is 46. The variance is 46. Finally we merged all these clusters. So in Watt's linkage, what you calculate, if you want to calculate the distance between two clusters, the distance between two clusters is nothing but the increase in sum of squared errors after merging. So these are the new distances that you calculate. Okay, so that is Watt's linkage. This is computationally not so much effective. It is intensive, but it is oftenly used in practice morely. So we talked about single linkage, complete linkage, average linkage, centroid linkage, and Watt's linkage. Watt's linkage is nothing but increase in sum of squared errors after merging. Okay, so this is how you calculated the increase in the distance between the two clusters. The distance between the cluster C1 and C is nothing but you calculated the centroid of both the clusters and then calculated the variance from that centroid and subtracted the new variance with the variance of the cluster, which will give you the increase in the sum of squared errors. Okay, so this is all about hierarchical clustering. In most of the cases, standardizing the data for hierarchical clustering is a good practice. Okay, so we haven't standardized the data initially. When you calculated this example, you calculated the data directly. You haven't standardized these variables, right? You haven't standardized these variables. Okay, it is always good practice to standardize the variables in the um, to standardize the variables, okay, for different patients. uh, Standardize the variables in the sense, so sorry, standardization has to be done this way, not this way. Standardize the variables this way. Okay, you have to standardize the variables so that the mean of them will be the same and standard deviation of them would be also be the same. Standard deviation is equal to 1. So if you look at this place here, so before standardization, before standardization, this is before standardization, and we already have created this cluster example here. We created this cluster example here, right? So if you look at this, this is the cluster that got formed. It merged diastolic BP and weight first, and then it merged with systolic blood pressure. When we don't standardize the values, but when we standardize the values using this Z score, we merged height and weight, and then we merged systolic and diastolic BP. So this looks like to be the right clustering, right? Height and weight are related to each other. Diastolic BP and systolic BP are related to each other. Okay, so when you standardize the variables, you will get meaningful clusters. Okay, so it is always good practice to standardize the clusters first. I mean, standardize the data and then apply the clustering algorithms or hierarchical clustering algorithms. Okay, yeah, that is all about hierarchical clustering. All right. Uh, that's all for today.